Greetings from Maui. Today, let's learn how to build your own large language model, or LLM. I'm a co-founder and CTO of Lamini. Before this, I co-founded MLCurve. It's a standards organization that helps companies measure performance of the fastest machine learning systems in the world. Before that, I was a founding engineer and eventually research lead in the Baidu Silicon Valley AI lab. We discovered many of the core technologies that are used in language models today, including scaling laws, which predict the performance of language models today. And my team there went on to build many of the language models that we know and love today, like GPT-3, GPT-4, ChatGPT, Llama 2 from Meta, Megatron from NVIDIA, Palm from Google. And before that, I was an architect on CUDA at NVIDIA. Today, we're going to walk through what it takes to build a complete application from scratch using a large language model. I thought it would be a good opportunity on a vacation while I'm more relaxed to build a completely new application rather than one that we're building for one of our customers. And I've always been curious about medical coding. You may not understand very much about this application, but we're going to walk through everything that it takes to start from an existing language model. Here we're going to use Mistral, and we're going to inject knowledge about a very specialized medical domain into it so that it actually remembers this as part of its weights. Now, this process is not easy. Building a complete application that's substantially better than one of these base models. It's not easy, but it's not impossible either. I think that what I found is that I can usually do it in about a week. And so I've spent about a week on this one so far, and it's gotten pretty good. So I want to walk you through all of the steps that it took to do that. I've seen a number of posts floating around online that say it's really hard to train your own language model. But that's not really what I found. So the way these posts will usually go is they'll say, well, maybe companies like OpenAI or Anthropic can train their own language model. But what most people, are claiming to do, when they say they're training their own language model, is actually not training their own language model. They're using a technology instead that's called RAG, retrieval augmented generation, where they're using an existing language model that's then just looking up information, kind of like how a human would look up information in a search engine, maybe an enterprise search engine over some documents that you have. But they're not, in fact, taking the information in those documents and having the language model actually learn that information. And I think the reason why this is happening is because, or why people are saying this is because it's actually pretty hard to do fine tuning. Like it's pretty hard to just take documents and then take that information and put that into a language model. There's a lot that can go wrong when you're doing that. So what I want to cover here today is a recipe to actually update the weights of the language model. We'll also see how technologies like RAG and technologies like fine tuning can coexist together. It's usually not an either or. Usually we want to use both of these to get the best and most optimized system. So let's see how that works. So we're going to follow an example that's inside of this Lamini SDK. So you can go to github.com lamini-ai/SDK. And the SDK here lists a few steps that we can go through if we want to train our own model. So the steps are listed out here. And this SDK is completely open source. So feel free to read any of this, change any of this, copy any of this. It's Apache 2 license, so you should be clear no matter where you are. Okay, so where do we start? So you see there's a lot of different steps in here. Again, we're going to try and go through this, and I'd recommend allocating about a week for this to go through all of these steps. We actually won't even get all the way through the end. I think we can get from step 1 to step 7. But we won't get into the much more advanced topics of domain adaptation or pre-training yet. But with this, we'll still get through a lot. So we'll get through the ability to connect a LLM up. to a complete application, integrating it with either a Slack, Python, or React application. We'll be able to perform prompt engineering so that we can craft a good prompt that changes the behavior of this language model, for the application we're looking at. We'll be able to add in retrieval. So we'll be able to augment the generation performed by the language model with retrieval from a text data set. We'll talk about how that works. We'll also be able to fine-tune the language model. So we'll be able to do what's called instruction fine-tuning, and we'll talk a little bit more about what that is. That actually updates the weights of the language model. We'll also look into how to extract structured output from the LLM. So following a guaranteed JSON schema, making sure that we can integrate the outputs of the language model with other parts of our system. We'll look into evaluation, like how do we know that the language model is performing well? And finally, we'll set up a filter kind of in based on a technology that's similar to DPO, direct policy optimization, and also similar to RLHF, reinforcement learning with human feedback. We'll use basically figure out how to refine our training data or add additional information to our training data to filter out the low quality data and to focus the model's attention on really the highest rated or the best quality data. And we won't have time to cover domain adaptation or pre-training. These things are just much more computationally intensive. And these are the things that, for example, if you were trying to build your own Mistral, Llama V3, GPT-5 kind of model, then you could go into these other areas. But they're also much more computationally expensive. And so, you may want to have, hundreds or thousands of GPUs allocated. But if you're just working on, steps 1 through 7, just a single machine should be sufficient. And if you're using Lamini, as I'm going to do here, you can basically get by with our just a single machine allocated. We're going to try to teach a basic language model. We're going to start with Mistral. We're going to teach it information about the ICD11 standard. This is the International Classification of Diseases 11th revision, WHO, World Health Organization standard. And this is really just a tool that if you've ever gone to, see a doctor or physician, and they've ever given you a diagnosis, you have pneumonia, you have COVID-19, there would be a code and a way of classifying that diagnosis in this system. So this is used both by healthcare practitioners, healthcare networks, also insurance companies, to determine how to code, how to document, how to bill, and how to record information about diseases that may, be relevant to people. So you think of this as having a lot of medical knowledge, and these standards are also highly complicated. So let's just look to see exactly what's happening here. So this is the main website of ICD11. We can look at the browser. So you can see, on the left-hand side here, it has all sorts of different categories of different diseases, like, for example, diseases of the skin, inflammatory, dermatoses, and I'm not a medical expert at all, so I have no idea what these mean, but they're actually fairly detailed. They typically have codes associated with them, so this is just the standard way of referring to, this particular diagnosis. And, there's some information about it. So one thing that we can usually do as a starting point when we're adding new knowledge into an LLM is we can ask, well, how much does the LLM already know about this? So let's go to the Lamini website and log in. And we can go to the playground and we can say, tell me about ICD11 code EB50. And this is just using a default Mistral model. And let's just see what happens. Ooh, okay, it's called other Specified malignant neoplasms of the digestive system. That's interesting. Okay, so let's see if that's right. I don't know if that's right because we were in diseases of the skin. Um, so it looks like, uh, sides of the neck and face. Again, I'm not a medical expert, but this looks pretty substantially different. And usually, what happens here when these models very confidently hallucinate an answer is that maybe they've seen a different version of a different standard, that had a very similar code. And so they match, something that's pretty close, but in this case is, highly incorrect. I think this is a good motivation for starting for this. ICD11 is a very new standard. These standards also change all the time. They're different by country. So uh, let's I feel like this is a good example, and we can kind of go back to the Lamini walkthrough and we can ask, all right, well, how do I take, maybe the knowledge from the ICD-11 standard and how do I inject it into the Mistral model so that the Mistral model will be more capable of answering questions like this, like talking about code EB50, or for example, helping a medical coding practitioner, like maybe someone working in a hospital, someone working in your doctor's office, someone working in a health insurance network. How do we help them get the right codes, for individual patients so that patients can be treated correctly and also billed correctly? So we're going to follow all of these steps. So let's navigate to the playground section of the walkthrough. Goal here is that we want to set up a playground. We want to be able to run a language model so that we can query it. We also want to do this in an environment that we can edit. So imagine that I'm, building a chat application that's integrated with a medical coding tool. I want to be able to actually call the language model from that tool. So how do I even do that? So that's the point of this section. So there's three different common ways that we've seen people do this. So one, you can call it from Python. This is going to be a common Python, command line tool. This is very common for machine learning engineers to use who are familiar working with Python. We also can see how to call this from a JavaScript, TypeScript, or React application. So imagine, you already have a web application and you just want to be able to call the language model from it. We can do that using this React application. And finally, sometimes, for internal communication, internal development, we see people integrating language models with internal communication tools like Slack. So the third example will show how to call a language model from Slack. Many of these things should generalize to other languages. Feel free to call, the language model from any language, any kind of web or application framework or any kind of chat application. Also, I'm going to go through these sections one by one. Feel free to just skip to the most appropriate section that makes sense for you. So, client. How do we call an LLM from Python? Okay, so this is pretty straightforward. So first, let's get a Lamini API key. Lamini hosts a bunch of servers that we're going to be using so that we don't have to stand up our own servers here in this tutorial. So let's click on this, go to the account page. It's going to log in. So I haven't logged in before in this account, so I'm going to log in. And I get an API key. So I'm going to grab my API key. When you just log in, you end up with a new user plan. If you want more credits, and we're going to blow through a ton of credits, send us a note. You can also buy this Pro plan, which is fairly cheap at about $100. Should give you plenty of credits to cover running a lot of LLM queries. Okay. Also, feel free to do this on a similar system or your own system. Okay, so now that we have the key, we can go ahead and install the Lamini library. And you can see that, just running the LLM is pretty simple. So you just import the library, you instantiate a runner for the model that you want. This is looking at a Llama v2 runner, so using Llama v2. And, we can run runner.call and ask it a question. How are you? And we should get a response like, oh, hello, I'm just an AI, blah, blah, blah. Okay, so there's also a few other ways of setting up that API key that we can look at. You can add it as an environment variable. You can add it as a variable from the Lamini library. We can also add it as a config file. Um, so let's look at, now that we've seen like the walkthrough for this, let's see how to actually do this in code. Okay, so I've checked out this repo, checkout. I'm calling this CPT GPT. CPT is another standard that's like ICD. Let's see. So let's look at Playground and let's look at the Python client. Okay. So one of the things before I do all of this, let's go into answers my API key. And we can just kind of see how this works. It's very similar to the example there. So we're going to call main, load questions. Here I've just stored some questions in a file. Sample questions.json lines. Answer the questions. I'm just going to loop over all the questions and ask them to this Llama v2 runner. And then I'm going to save them question and answer and write them all into an output file. So let's see what happens. Also, just note, and I kind of want to mention this a bit, you can just call this from Python, set up your own Python environment and so on. I personally like to use Docker to set up an environment just because it keeps everything clean and reproducible. So you also see in this folder, there's this folder that's called Dockerized Client, where there's a script called answer sample questions. We can look inside that to see what's happening. So there's a lot going on in here, but basically it builds a container, builds a Docker container, mounts the data directory, and then runs the Docker container. Okay, and we can also look at the Docker file to see what's happening inside that container. Not a whole lot, starting from a base Python 3.11 image, adding the requirements. So now we're getting a Python environment that's clean, and we're copying all of the source code that we have into this container. So answer sample questions was the only source code that we have. We have some scripts for launching this that we could look at in a second, and the data, the sample questions. And the entry point just calls this start script. But what is the start script? That looks a little magical, so let's look inside the start script. The start script is running inside the container. It just sets up the Python path and calls Python on our script, answer sample questions. There's another script in there that's maybe worth looking at. We saw that in there. It's called build. This just builds the Docker container. So every time we run the program, we rebuild the container just in case any of the source code has changed. So build, Lamini Python client, and then we're pointing it at the right Docker file and the right Docker build context so that it has all of the information that it needs to build the container. Okay, and that Docker build context, by the way, is pointing right here at this directory. Okay, so we can try running that, Dockerized client, answer sample questions. So now it's building the container, installing Lamini. So I guess I haven't run this in a while. So again, if you're not doing this in Docker, and do pip install requirements.txt in your own environment, whether you use Conda, you use a virtual environment. Okay, so we're running. While we're doing that, it might be interesting just to look at some of those questions. Okay, so you can see the questions are starting to get answered. Um, let's just look at some of those questions to see what's happening. Sample questions. Okay, so turns out I went through the ICD11 standard and wrote down some questions. Tell me about code 03. Tell me about JA42. Tell me about LD90.3. So that's kind of what's being asked here in the script. So it's about halfway done. Looks like it's going to take about 1 minute. One thing to note as we're doing this, of course, is that, language models are pretty expensive. Calling language models, serially like this, like one question at a time, um, it can take a while. Some of these queries are pretty long. You might have experienced this, like, for example, you go to ChatGPT and like type in something and it starts printing out, but, for a request made from a client like Python, you have to wait all the way until the end before it finishes, before you return the answer. Um, like typical request times, for example, for like GPT-4 can be 30 seconds, 60 seconds. They can be pretty long. Um, these models are a little bit better. Looks like they're about 10 seconds, maybe 8 seconds, um, but still pretty long, just in terms of latency. So we'll look at how to address that. Typically, it's hard to substantially improve latency, but it is possible to substantially improve throughput. So we'll look at that a little bit. This, example application doesn't do anything fancy at all. There's no optimization. Um, so if you just look at it, it's in a loop. It's just calling the language model serially, like one at a time. So there's no parallelization. There's no throughput. And that's why it takes so long. So, but that's okay, finished. That wasn't too bad. Um, we got some data. And just as, we saw in the original example, most of the time the model just does not know like what this is, or it hallucinates it completely, right? Like JA42 is a legislative text amendment. Not really what I was getting at. So, uh, okay, that's a good step though. Now you know how to call this from Python. We're going to learn how to call the LLM from a React web app. So we're in Playground tutorial, and let's click on the React tutorial. Okay, the first step is to get the Lamini API key. So let's go here and do that. Logs in. There is the API key. Go back. And where do we put it? Well, there's a file, home.playground, playground config. This is something that we're setting up just for this React web app. So let's do that. Playground, playground config. Okay, we've already created this. And let's paste in the key. Okay, so we did that. Now start the playground. Go into the playground directory and run chat playground up. Do that. All right. You'll notice that this runs the entire playground inside of a Docker container. We'll look more into that in a second. So it's still starting up. This takes a little bit. Now it seems like it started. So last step, we should be able to navigate to localhost 5001. Do that. Localhost 5001. So it's a local development environment. All right, and hopefully we can ask it a question. Tell me about the ICD standard from the World Health Organization. Let's see what happens. Ooh, it looks like it's undefined. Oh, wait a second. There we go. A standard system of coding and classifying diseases. This looks about right. There's ICD-0, ICD-10, 10th revision. Okay, so now we have a functioning playground. let's look a little bit deeper in to see how the code works. All right, you can see a lot of logging messages, but let's just kill that. And let's just look at what's happening here. So React apps are a little bit complicated. We're not going to cover absolutely everything that goes into a React app here, but let's look at a few important pieces. So let's look at our start script. Start script is pretty simple. It builds a Docker container with the web app in it, has both the front end and the back end in there, and it starts that container. There's also some port mappings. This was the one that we were using. It mounts a few directories. So it mounts the playground directory and the source directory. We'll look at what those are doing in a second, but this is so that the development environment does auto reload. So if you change something in your editor, it will reload the website. And of course, we created that config file with our key in it, so we mounted that into the container. Okay, let's look at a few essential pieces of this app. There's a lot going on in here, so again, we're not going to cover everything. Let's look at the Docker file just to see what's inside of that container. So it's got Python in there. The Python is used for the web backend. We've also got npm node and yarn to build the React app. Okay, so we've got Python source code for the backend, got some Python requirements, and we've got a lot of React source code for the front end. And that's pretty much it. We just copy the source code in. It's also worth noting here, there's this package.json. This is using yarn to install all of the front end dependencies. And then we'll also have requirements.txt using pip to install all of the Python dependencies. This should completely work fine if you want to build this outside of Docker. So you can run yarn in your own environment, run pip in your own environment. This should work just fine. Okay, we just package it with Docker. I personally like Docker because there's so many different ways of messing up an environment. Okay, let's look a little bit more into what's happening. Okay, so let's look at the front end source code. Okay, so the entry point here is app TypeScript. And this app does almost nothing. It just instantiates this playground component. So we can look to see what's happening inside of that playground component. And the playground component is maybe a little bit more complicated, but it has a drop-down menu for models. And it has a settings pane, and it has this interactive playground, which is that text box that we were looking at. That's this thing here. So we can look at that one a little bit. You can see we pipe through some examples like the token or the selected model. Let's look at what happens inside that interactive playground. I have no idea what happened there. But let's look at this file. So this interactive playground is also pretty straightforward. You can see we have some state, which has the message that the user has typed in, and we're recording the chat history. So you can see that there's, when the message gets sent, we're going to call this send message. And here's where all of the action actually happens. So fetch streaming inference. All right, let's look at our fetch inference, which has fetch streaming inference. It really calls fetch streaming custom. It's right here. This is where a lot of the really interesting stuff happens. So here we have a prompt. You can see there are different prompts for different models. Llama 2 prompts, Intel neural chat prompts, Mistral prompts. And the question is coming in here. So the question is getting added into the prompt. So the prompt is getting, the user query. We'll cover prompts, in the later section, but this may be a first introduction. And then we're forming the request here. It's also worth noting there's some polling logic. So you see how the chat window kind of refreshes every so often with a new result. This happens from polling, and it uses this streaming interface. So, okay, this is the actual request. We're calling fetch. There's a API URL, which is just API.lamini .ai, and then streaming generate. So we post, we get the body, the parameters. We have all of our different parameters in there. This is our body, model name. The output type is a string. Put in the prompt, put in the max tokens. You call this, and then the response comes out as JSON. There's all sorts of different status codes. You can see error handling. And we add on the partial response. The rest of the logic is just polling, and that's pretty much it. So that's how that component kind of gets updated in real time there. Okay, that's one thing that's worth looking at. It's also worth looking at the backend. So now, okay, that was calling, okay, our app, streaming generate, or this is our own app, streaming generate. Where does that API endpoint come from? Well, now we're going into React LLM Playground, the Playground directory. Inside there, there's Fast API. Fast API is a web server. So let's look at this web server. So, okay, how does this work? We're going to do setup and run server. Creates a Uvicorn instance. Uvicorn is our Python web server. We're going to basically start up that server, and we're going to look at run server. So here it has some build front end logic. The front end logic basically rebuilds that React web application and then mounts it. So here, this is building it, and then this is mounting it as a Jinja 2 template. So basically this is just compiling all of those TypeScript source files into static front-end source files, and then it's mounting it here so that we have basically the entire application served from the same server. So this is serving the front end from this Uvicorn web server. And then we're also going to run this main, which is going to run a fast API endpoint. So this is going to run task 1 here, which is create API. And that's going to run main API app, and run this Uvicorn server on it. Okay. And so we can actually see where this app is coming from up here. Okay. So let's look a little bit closer. So playground, fast API, chat backend. That's this file here. So we can look here. So this is creating a fast API app. Turning off cores, always important to turn off cores. And this is the endpoint. So here we're declaring this post endpoint called streaming generate. Remember, that was the thing that we called from our React front end. Streaming generate, right here. Okay, so this is a very lightweight backend. This backend does almost nothing, but it does show you that you can basically edit the request, and you can change the way that the LLM is called. So the LLM is getting called in here. So the first thing it does here is it does prompt editing. So we're going to actually change the prompt. And this has a very, the default here is a very straightforward prompt, which is, oh, you're a helpful assistant. Maybe not that useful. We'll look at that in the prompt engineering section next. Okay, so we're maybe updating the prompt here. And then what happens? Well, we're calling run streaming inference. And what is that doing? Well, this is just forming a request um, to the Lamini streaming completions endpoint. So config URL v1 streaming completions. Key? Well, that key came out of our file that we just put here. There's our key. Um, and that's just forwarding the request. So the main idea here is that, we have a backend, we have the ability to edit this backend, we can also edit the front end, and we can call an LLM of our choosing. Okay, so remember over here, we're calling fetch in the body. We are selecting the model name, so we can call a model of our choosing. We'll see later that we're able to change this to these, kind of built-in models, any model that's on Hugging Face. This is the string that I get from Hugging Face. So let's just look that up if I want to figure out how to call that. We go to Hugging Face, Mistral instruct. There's Hugging Face, Mistral instruct, and here is the string that I can just copy. Which you'll notice was that string there. Right, the same one. And you could do that for any of the models on Hugging Face. There are quite a lot of them. 450,000. Okay. So hopefully that gives you an introduction to how to run a web backend and front end that calls an LLM. So from here, you should be set up to be able to edit the LLM. Let's learn how to call an LLM from a Slack bot. So it's pretty easy to call an LLM from Slack using Lamini. So first, let's get our API key. Okay, good API key for us. When you log in, just note that you get one of these Lamini free plans. Lamini has a cluster with hundreds of GPUs in it so that we can run all of these different models and all these different requests. We do rate limit new users just so that we don't get totally overwhelmed. If you need a lot more access than like the default allocation, just let us know, send us an email. You can also press this button to buy a pro plan, which has about 10,000 requests for about $100 and a free month. So check it out. Feel free also to use your own LLM. Okay, so let's look at the Slack bot. So now we have the Slack bot. We have our API key. We basically need to fill out this config file here. So in the slackbot directory, I went into the SDK, playground, slackbot. Inside of the Slack directory, there is a config file. This config file has a bunch of important information. So this is for connecting to our bot, connecting to Slack, and our token. So this is the token that we just got from Lamini. So let's fill that in here. Okay, but where do we get the rest of this information? Where does this token come from? Well, we just go to Slack. So here I have a channel. I can just click on the channel and I can look into Where is it? Oh yeah, all the way at the bottom. There's the ID, channel ID. Okay. Next, I need to get, okay, so that was, oops, there's this channel ID here. I also need to get this bot token, this app token. So where am I going to get those things from? So I need to go into Slack. So let's open up Slack admin. I have to have a Slack admin. I can basically make a new app. So I can press this button, create new app. There we go. I can click on the app. You need to add a bunch of functionality and such to your app. So I have to have a slackbot token. So here's one that has connections. So I can generate one. Can have connections write, connections read, app configuration write. There's the slackbot. Oh yeah, and there's my app token. That was the app token that we just saw. That app token. Okay, I also need a bot token. Let's see, so I go over here, there's OAuth and permissions. Down here, oh look at that, there's the bot token. Note, every time I press this button, reinstall the workspace, I gotta get a new token. Okay, so there's that. Now finally, when I created this app, I need to give it all sorts of permissions. So you can see all these little permissions on here. I gotta give it permissions to read mentions, to read calls, to read history, to write, to read emojis, to read the history, read reactions. Just press this add OAuth scope button and then just add all of them onto your bot. And I think that is it. I'm pretty sure that is it. Okay, after we do this demo, I'm going to reinstall this to generate some new tokens. But that is the app tokens. So now I can run this bot up script, and that will start a Slack bot running in this computer. Look, it's running. Okay, we're using this library called slackbot, which is a Python library for Slack that makes it pretty easy to write Slack apps. So let's see what happens. Okay, I've installed this thing already. I'm just gonna say hi, hi, and it should start typing. Oh, and it says, hello, how can I assist you today? Great. So I've set up my first Slack app that I can talk to. Now let's look a little bit more into how does this thing even work? Okay, so let's kill it. And just know it has to be running while you're talking to it. So now that I've killed it, if I start talking to it again, it won't work, right? It will just sit there and not do anything. All right, so let's see how this thing works. So let's look into this start script. What does it do? It creates a Docker container, builds a Docker container, and then it runs the container. And this thing is pretty simple. It just maps this port 3000. And I think that's all that we really need. I don't even think we even need this line. But let's look. What's happening inside of that Docker container? All right, so we're installing Python, installing some requirements, and then we're copying all the source code. And then we're running in the start script. So let's look to see what's happening. So inside of our requirements, what did we install? Well, we installed slackbot and the Slack SDK. And we installed Lamini. So slackbot, the SDK, obviously for talking to Slack, and Lamini to call the LLM. All right, other things that were going on there. There was also a start script. What does that thing do? Well, it just calls Python on the Slack app. That's pretty simple. What does the build script do? Build just runs Docker build. So it just builds this Docker container. I think that's everything so far except for the app. So let's look at the app. All right, inside the Slack directory, there's an app.py. Let's take a look at it. So import Lamini. So we can call Lamini models. We import a slackbot app and a socket mold handler. Remember, we had a config file to get that key out of. This is where we load it. You get some tokens, the bot token for Slack, the Slack bolt needs that. Um, and then there's just a bunch of handlers in here. So, for example, when this thing is mentioned, when the Slack bot is mentioned, it's going to get the channel ID. It's going to figure out what was the question or what did the user type in. And then it just iterates through all the models. So inside of the config file, there is a section called model names. Let's just look at that just so we can see. Fig. Okay, model names, right? There's a list. There's only one thing in it, Mistral, the Mistral model. Okay, so that got the model names. Now we're just going to loop over all the model names and try to respond. All right, so it says say typing. Okay, so that looks like the model is typing. Then we're going to ask the model a question. So we're going to see what happens there a little bit later. It does a little bit of post-processing, and then it basically just this here. So client chat update. It just prints it on there, prints the text that it got out of the LLM. Okay, but let's look at this ask model question function. Okay, here's where it gets a little bit more interesting. All right, so it's basically making a request to Lamini. So here's a token. Okay, it's going to get the token. That's our Lamini token, so that we know which user we are. All right, we're going to form a prompt. So this section in here, oh, you are a medical coding expert who read the ICD11 standard. Okay, so that's maybe default prompt. There's also, we'll get to this a little bit, but basically we're putting together a prompt. And then we're creating a body of the request. So we're going to give it the model name of the prompt. The ID, you can call it whatever you want. Now we can call this API.lamini.ai v1 completions API, and we'll get an answer. And that's it. So that's everything that you need to do to start a Slack bot, connect it to Slack, ask it some questions. The Slack bot has a handler. It's going to respond to times it's mentioned, and it's going to submit a request to Lamini, to an LLM, to complete the sentence, and then we're going to get the response back. If the response is good, you pull it out and update the chat with it. So that's pretty easy. So that's just shows how easy it can be to wire up a language model, into a bot like a Slack bot. Next up, let's look a little bit closer into how to make a good prompt. You saw a little bit of prompts in there, but what's really going on there, and how do we change the prompt so that the model performance improves? Let's take a look at that next. Now that you're able to run a language model, it's time to learn how to prompt engineer a language model. Prompt engineering is incredibly important. We're going to use it all over the place. So you need to get this down. Prompt engineering should be pretty fast. You should be able to edit the prompt of a model to get it to change its behavior in a really short amount of time. So maybe a few minutes you should be able to write a prompt. If you really want to spend a lot of time optimizing a prompt, you might spend a few hours on it. I typically wouldn't spend more than maybe 3 or 4 hours on it. If you're spending more than a few hours on it, you probably reach the point of diminishing returns, and you should move on to do something else. So let's look at prompt engineering. What even is a prompt? Well, remember language models. Remember, they're very simple. They're text in and text out. So the text that goes into the language model is typically called the prompt. Models that are instruction tuned, or like ChatGPT, they're able to follow users' instructions. The prompt is usually just some instructions telling the model what to do. So here are some examples here. How do I convert inches into centimeters? Summarize a story, and then followed by the story. Write a Java program um, uh, to return the indices of two numbers that add up to the target. Write a short story about a bear. So there's all sorts of different things you can ask a language model to do using a prompt. So prompts, right here, they look pretty simple, but crafting prompts is not always simple. There's a little bit of an art to it. So I'm going to try and cover a few just guiding principles here, and the idea is like at the end of this, we should be able to use a change the prompt of the language model so that it actually changes the behavior of the language model. Um, if you remember before when we were looking at our source code, I'm just going to pick the slackbot, in this example. Um, when we called the ask a model question function, we have like the user's question in here, but there's some extra stuff in here, which is what we're going to call the prompt. So just by editing this extra stuff in here or the prompt, we can change the behavior of the language model so that instead of just, maybe being a helpful assistant, which might be a default that, many existing models might have, you can change its behavior to do something different. And changing its behavior is as simple as editing a string. But you have to know what to put in the string, and that's why we have to look a little bit more into a prompt. Okay, so there's a few common mistakes that I see people make when they're editing prompts. So I just want to put them up front and center because if you mess these things up, your performance of your model will be absolute trash, and you will have, it'll be very unobvious of like why the model is performing like garbage. So um, let's cover them first. So here, the first one, you must follow the prompt template syntax, which is different for every model. So, oh, you're using Llama v2? Well, you need to use the Llama v2 prompt syntax. Oh, you're using Mistral? You need to use the Mistral prompt syntax. If you switch them up, if you forget this, model performance will absolutely go off a cliff. Like it will be just completely, like it'll still do something like it might make sense, but if you just look at the evaluation of the model, all of your metrics will take a huge hit. It might be like a 20% or more like hit in accuracy of like a number of questions that you get right kind of accuracy hit. It's a huge accuracy hit. So you need to make sure not to screw up the prompt template syntax because if you do so, you will get no error message. The model will never tell you that you're doing it wrong. It will just perform worse. So what even is the prompt template syntax? Let's look at that section first because that is something that if you screw it up, it will absolutely mess things up. And it's also weird, right? Like, okay, so here's an example of the Llama 2 prompt template syntax. You need this special, S token. You need this special instruction token. You need this special like sys token. Like, why do you need all of this stuff? This seems really weird. Like, what is the point of all of this stuff? The intuition behind this is when the language model was trained, it was trained on data in exactly this format. So the first token was always the star token. The next token was always this instruction token. I guess this is meant to indicate the beginning of the command or the instruction, like what you're asking the language model to do, and so on. You may or may not have this system prompt, but the point is like if you if you mess up this stuff, if you don't include these tokens, you're basically changing what the model is seeing when you're evaluating it versus when it was trained, and that's a bad idea. So just a common thing in machine learning. This is a core principle of supervised learning. It comes out of the IID statistical distribution principle, which is that the input distribution or the training distribution, like the distribution of data that I trained my model on, should match the distribution of data that I'm evaluating my model on. And if there are assumptions, like for example, that my input data when I was training my model follows exactly this format with exactly these tokens in exactly these places during training, I better match that uh, during inference or when I'm actually running the model or when I'm doing prompt engineering. So that's why you need this. And it turns out that this is highly different, for different models. As we're looking at here, this is the Llama 2 template. And oh, look down here. This is the Mistral 7 billion parameter template, which kind of similar, but also different. So like in particular, Mistral doesn't have a separate system tag here. Um, So I would strongly recommend if you're using a new language model, you should go and look up either in the paper on the Hugging Face model card or something, just go and figure out exactly what the prompt template was. And make sure you stick to that prompt template and don't mess that up. So this is something that's actually very hard to test for because again, if you screw this up, like, oh, I forgot the start token, or oh, I forgot to close this instruction thing, or I had a typo somewhere. Well, guess what's going to happen? The model is going to just silently perform worse. So you'll probably be able to detect something like this once we get metrics set up, but metrics are going to come later and they're even more complicated. So, the starting point, just try to stick to the prompt templates. In just as a side note, this is why in Lamini, let's just look at our docs. In the docs, we have these concepts of um, we have the concepts of runners. So runners, when you call like, oh, LLM runner.call, how are you? Well, this stuff is going to get automatically inserted for you. So these runners basically have prompt templates that are just canned for you so that you don't really have to think about it. So if you don't want to, think about this, we definitely recommend using one of these like canned runners, or if you have your own model and it uses a different prompt template, you might want to make a runner and validate it, to make sure that it's working correctly. Okay, so that's the prompt template. You'll also note that there's this concept of like a system prompt in some things and a user prompt. That's going to lead us into the next section. So let's go and look at what comes next. Okay, so the first thing, just remember the first thing, don't mess up that prompt template. Okay, we've got the prompt template down. Now we can look at what else goes into the prompt. So we've seen prompts often follow this kind of format. Um, they'll usually have these at least these 5 sections in there. There may be even more in there. Okay, so um, we're going to go through these sections and just make sure that you understand these, like how to write each of these sections and like what to go into them. But before I do that, I want to mention the second most common mistake that people make with prompt engineering. Okay, so the second most common mistake, um, it's it's this one. Okay, iterate and repeat. So it's important to note prompt engineering, just like all of machine learning, is iterative. That means that you should not be sitting there and spending more than 10 seconds writing your prompt. You should not be just like sitting there, going and looking up in a reference manual, like, okay, is this prompt perfect? Can I change this part of it? Maybe I can tweak this particular aspect of it. Don't do that. Instead, set up an iterative flow, a flow where you can quickly change the prompt, run the model, and look at the results and get feedback of like, did this change that I made to the prompt actually help? The speed that you can go around that loop determines the speed that you can actually improve your prompt. So you want to iterate not once, don't just sit there for 4 hours crafting the most perfect possible prompt and then finally, after 4 hours you can submit it for the first time. Try to make like 100 changes. Try to edit the prompt, have all different ideas of like how you could change the prompt, edit it like 100 times in 4 hours and try it out. Try running a bunch of data through it. Try running a bunch of queries with it. Start interacting with it. Try and break it. Um, if you follow an iterative approach, you're going to end up with a much, much higher performance prompt than if you just sit there and think about the best possible prompt. Okay, so there's all sorts of different ways we can iterate, and we'll get to that in a second. But I think the second biggest mistake that I people see people make with prompt engineering is that they don't even think about iteration. They just like go off and take like 2 days to write a prompt, and then they come back with a prompt, and then it's not very good, and then they wasted 2 days. With instead, you probably could have figured that out in 10 seconds. Also, just as a side note, that's the reason why we set up a playground in the previous example. So let's just look at this. All right, I'm back to my Slack bot. Remember from the previous example? Okay, I can run bot up. Okay, now assuming it runs. All right, it's running. Now look. Oh, you are a helpful assistant, a helpful medical assistant. There's an idea. Um, well, I just restarted my Slack bot with a new prompt and I just redeployed it and it's running in Slack right now and I can ask it a question. So I iterated on it. How long did that take me? About 10 seconds. I want to be able to iterate on prompt engineering about that fast. Faster the better. Okay. So that's the second biggest mistake that I see people making with prompt engineering. Okay, let's keep going. So let's go back and let's review our prompt sections. So the next thing that I see is that just people are not necessarily aware of all of these different sections and why they matter. People usually get the first section, like a description of the task. That one's pretty straightforward. For our ICD11 example, let's just say I can describe a task of, you are a helpful medical assistant who is versed in the ICD11 standard, um, and you're going to help a user, go through doctor's notes and figure out the right codes, for this particular patient in this particular situation. So, you can just write a very high level task description like that. That's pretty straightforward. So the thing that I think people usually miss is they miss the second section. So they miss task parameters. Um, so let me try and give an example of task parameters and like why this is so important. Okay. So let me try and draw the distinction between two situations. Okay. So let me just go into Google and like type in the Google just search engine. Okay, you can see all my search history. Hooray. Um, let's see. Um, let me pick an example just to kind of demonstrate what happens if you don't have task parameters. So let me just type in a query into an open-ended interface like Google. So I can say, okay, here, write me a function to parse arguments. Okay, let's see what that does. How do I parse arguments? Okay, I get some like very general answer on Stack Overflow. Great. So that's an example of something where I have no task parameters, right? Okay, I didn't have task parameters. I just had basically the query, but I had no other information. I have no idea what I'm doing. I just had a query. This was my query. Write me a function to parse arguments. Let's look at a different system that actually incorporates task parameters. So I personally like using GitHub Copilot. I use GitHub Copilot all the time. GitHub Copilot incorporates task parameters. So let's just pick an example. Here's some source file that I was playing around with. We'll get to this a little bit later, but this is some source code that is used for a later step here in the SDK for classifying data. Okay, let's say I want to have a very similar query. So I want to say parse command line arguments. So very similar query. What's the difference here? Well, did you see it auto-completed that? Okay, now if I go up here, I try and type in import. I can start actually arg parsing. Let's see what happens. Oh, look, parser equals argument parser. Oh, look, it's actually getting the path. Look, okay, I can actually get the arguments. Now maybe I can pass my arguments into my load examples function. I can actually take this as a parameter rather than hard coding it. Okay, that was much more relevant, wasn't it? That was very specific and very helpful for this real application. How is the model able to do that? It has task parameters. What are the task parameters? Well, GitHub Copilot knows that I'm in this source file. It knows that I'm in calibrate.py. When I typed in this command, this query, right? Parse command line arguments. It has all of the extra context of like this source file. It has all of the code in this source file. So how does that actually work in GitHub Copilot? Well, there's a section of the prompt that takes all of that information. Those are task parameters. Um, there's a huge difference between like a very open-ended interface where it could be anything, ask me anything. Google, people could ask Google anything. There's a place for ask me anything interfaces, but there's also a place for, very specific, very focused interfaces where you just know a lot about the application. Like let's go back to my medical coding example. This is if I was building a real, medical coding application, I would have the entire patient's health record. I would have their chart. Um, I would have like a form that would be filled out of like all of the extra information about this diagnosis. Maybe some pieces of it I'm not sure about, but there'd be a lot of information. Like I'd have test result data. I'd have the conversation with the doctor. I'd have, what is like the inbound, like the triage. There would be a ton of stuff like that in there. That would all be in a database. There would be an app that would have all that stuff. And I could pull all of that stuff and put it into a task parameter section in my prompt. And a model that had access to that information would do vastly better, just be a much easier problem for that model than a model who was okay, how should I diagnose Bob? Who the hell is Bob? Right? How the hell is Google supposed to know this? Google has no idea. But if I was in an EHR application, I know exactly who Bob was. Um, so that's the difference. I think, as I was saying, like people one of the biggest mistakes that I see people make when they're building prompts is that they're not like understanding that distinction, or they're not like taking that distinction into account. They're not filling out this section. They're not taking advantage of all of the task specific data that they have available to them in their application, and making that available into the to the language model. And just imagine what that would be like if you were actually building a system like that. Well, okay, I need to pull Bob's EHR record. That means I probably need to, in my backend, in addition to connecting to the LLM, I need to connect to the EHR, and I need to be able to pull parameters out of it. And I have to have some function that like joins all of that, data together into a prompt. Um, okay, and we've kind of given you a template in the Slack app here. We're like, oh, right in the body of this function, you could think about pulling all of that data and getting it available here. So, um, okay, so we've covered a few things. You got to get the prompt template syntax right. You got to iterate fast. This section in particular, task parameters, people often miss this. They just don't even think about it. They go straight to an interface that looks more like Google, write me a function to parse arguments, and then you get an answer like this. Um, okay, so there's a few other things that are going to be important here. So Uh, the next section here is also important. So training data. What does that even mean? So there's a technology in machine learning that's called few-shot learning. And the premise of this kind of technology is that as you give the model more data, it gets better. Like it gets more accurate. It's almost like even like a human, like here's a few examples of the task, so that in addition to the explanation, like the task description, you can also see just some examples of what you want the results to look like, for particular questions, what are the answers? Um, adding a few pieces of data improves the accuracy of the model. That's why we have this section. So it's helpful to include some training data in the prompt itself. But we're not training the model, we're not updating the model's weights, we're not doing backprop or anything like that, but we are providing extra information to the model through training data that can improve the performance of the model. So training data is important to include in your model too, and we'll look at that, what that actually looks like. And then finally, there's this section on retrieval augmented data. We'll cover this in the next section, but the teaser for the next section is, well, we may have a lot of extra data that just is not going to fit into this prompt. If the prompt was unlimited size, we could probably fit all the data that we have in here. Why not throw all the data that you have in there? Well, the reason why is because prompts have a limited size. Um, so we could actually, I think there's a section on this. Um, training data. Okay, here we go. So there are two reasons why, like, why do prompts even have limits? Why can't we put as much data as we want in there? Um, I'm going to say this a few times, but prompt engineering is often a trade-off between packing all sorts of like relevant, useful information into the prompt that improves the model's performance and running up against the prompt size limitation because you can't pack everything in there. So you have to choose what goes in and what doesn't go in. Okay. So why do we have to choose? Like, why does this have a limitation at all? I've heard that models, I might have read a research paper, some models have 1 million token context. Well, there's a kind of a couple of reasons why. Okay, so one reason is a computational reason. So when we run this model, the prompt gets converted into a tensor or just a giant array of floating point numbers. And it takes up a bunch of memory when I do this. Um, so a really long prompt, also when I'm like unrolling the model over like a really long prompt, it just takes up a bunch of memory. So eventually I run out of memory. Also, as the prompt gets really long, I'm also asking the model, like in the query, to read the prompt. And that's computation. Like the LLM, you saw the query times are pretty long for LLMs. LLMs have a huge amount of computation. It's like, billions of floating point operations per token. It's really expensive. So if I throw a ton of tokens in there, a really long prompt, well, there's more computation. So both memory and time. If I have a really big prompt, it's going to be more expensive. And real systems, eventually, they're going to run out of resources. So the systems that we run these models on have a finite amount of DRAM, finite amount of like GPU memory. They eventually run out of memory. They also have a finite amount of time. Like we don't let people run queries that take forever. So we put time limits on queries, and those impose limitations on the prompt size. So that's one reason why we have um, limits on the prompt size. There's another technical reason of why we have limits on the prompt size. So it turns out that when I'm going to go back to this principle over and over again of supervised learning, IID. The training distribution should match the test distribution. Well, if we train the model on data with prompts of particular lengths, um, and then we evaluate the model on prompts of very different lengths, well, this kind of goes out of distribution. That means that the model hasn't really seen anything like that before, and so the model's performance is usually a little bit worse. There's all sorts of machine learning technologies that try and mitigate this, but they really mitigate this. They don't fully eliminate this. This is related to what are typically called position encodings, which are how models like transformers tell the order of tokens. Like, is this the first word, is the second word, or the last word? They use position encodings, and position encodings are not always invariant to very large sizes. You may actually have to change the way that you do position encodings if you change the model length. And for a model that's already been trained, that might mean retraining that model or at least fine tuning that model. Um, so practically, models have size limitations on the prompt. If you're curious to like look at the size limitations, you can actually usually go into the visit Hugging Face. You can look at in models. Like imagine I went to this Mistral AI. So this is the model we're using. So just look at this one. Okay, I go to the main model page. I go into the files and version sections. There's a config file in here. This config file has like all sorts of parameters in it, but this one in here, line 11, max position embeddings tells you the number of tokens that the model was trained with. Like this is the max number of tokens that you can put into the prompt. It's actually the prompt and the result of the model. The model generates some text on the output. It's the input plus the output. That's this number, 32K. For this model in particular. And if you're curious to see what this is for different models, you can go in Hugging Face and find the config file and look up this value. It's usually the same thing for transformer models, max position embeddings. Um, okay, let's go back. All right. Okay, so that's how we came up with the limit. So again, prompt engineering is almost always a trade-off between cramming important information into the prompt, and fighting against the limit, the size limit. Okay, and again, it's perfectly fine to do it iteratively. Try, starting out with a blank prompt, add some data, add some description. You have to make some space also for your actual query. Um, and see what happens. Eventually you're going to run into a limit. We'll give you an error message. You typically get an error when you hit the limit, and then just back off from the limit. And that's typically how you do prompt engineering. Okay, so we talked a lot about it. Why don't we actually go through it and try it out? Okay, so again, I'm going to start from this slackbot, just because it's pretty easy, but pick whichever one you want. Okay, so we're going to look at two examples here. So this was the original one, okay? And actually, if I remember right, I think this model, if I look at this, okay, it has start token, instruction, system prompt, answer the following question. This is Mistral. Um, okay. So again, the base model is pretty simple. So again, this is the system prompt. This is what we were calling the task description previously, your helpful medical assistant. And then the complete prompt is this string. Don't forget these things. That's part of the prompt template. Insert this string here. Answer the following question. Here's the question. So we call this section typically the task description. And this is just a simple starting point. Okay, so I'm moving over into the prompt engineering section, and I added a bunch of other stuff in here. Okay, so one thing that I did here, system prompt, you are now a medical coding expert. This is something that is a common form in the task description. It's both telling the model about the task, and it's also telling the model about the person that the model should be imitating. This is probably a little bit of a strange thing, but if you tell the model you are a pirate, it will start talking like a pirate. If you tell the model you are a 5-year-old child, it will start talking like a 5-year-old child. If you tell the model that you are a medical coding expert, with 20 years of experience at Mayo Clinic. I don't know if Mayo Clinic is good, but like something that's good, and you have read the entire ICD11 standard from the World Health Organization, the model will act like that. Like it will act like whoever the persona is that you're telling it is. So, important part of the task description is the persona. All right. You can also give it some information. So you're asked to code the following medical report. If you don't know the answer, reply that you don't know. We also typically want to give a size limitation so the model can, a common issue with models is they just run on forever. So let's see, answer in 3 sentences or less. Okay. So that's the task. The next thing we might have here are the task parameters. So again, like maybe we have like additional information. Maybe we have some information about the provider, about the patient. I'm really just making this up because I didn't build a complete coding application. But the idea here would be, okay, healthcare provider, like let's just say what we normally do here. Say healthcare provider. I would say get healthcare provider. Patient name. Eleanor Williams, maybe not. Get patient name. Year. Get year. I programmatically fill out this section. So this section, system prompt, or we can just rename this one task description. Make it easier to understand. Task description, Task parameters. Task description is typically fixed. Task parameters variable depending on, again, like what is your application? And then answer the following question. Okay, seems fairly straightforward. But wait, there's more. Add training examples. Okay, so now we're getting into this section here, adding in training data. We understood why we need this few-shot learning. What does this even look like? Training data in the context of these chat models typically looks like fully formed, uh, fully formed queries. So like, or fully formed instructions. Like this is like, okay, start, here's instruction, end of the instruction. Now the model's going to generate the answer, and it's going to end this with a stop token or end of sequence token. Okay. Training examples are basically just references. So here, healthcare provider, here's some training data. I just made this up, but just to give you an idea of like what training data could look like. Okay, task parameters. The healthcare provider is Mayo Clinic, patient name is Sarah Williams. What is the diagnosis for alcohol-induced anxiety disorder? Okay, that's the question. When we have data here, when we have training data, we typically include the reference answer. So here I have the answer, which is the code. Hopefully that's correct. And here's some context information. Like maybe this is just information about alcohol-induced anxiety disorder. Okay. And then I have a number of examples like that all in an array here. And I have this function, add training examples, which I wrote down here, which basically just takes the same prompt format that we had up there, and it just makes a whole bunch of complete prompts, including, the task description, the parameters, the whole thing. But also importantly here, it includes the answer, and it actually includes the context at the end. So it gives the answer, the model provides the actual code, the answer is the code, but it also produces something like an explanation of like why it coded it in this particular way, or more information about the code and like what it means, so that the user might have some extra information. Okay, so then just basically forming a much longer prompt that has a bunch of these examples in front of it. Okay, so now that I have all of this there, let's try running it and see what happens. Okay, so I'm going to move out of the playground section into the prompt engineering section. I have another slackbot up here, which I've also set up. Let's just run it. All right, look. See if it's working at all. Oops, of course, it's not working because I didn't actually fill in these functions, get healthcare provider, and so on. Well, let's fix that. All right, let's try that again. So we made a mistake. That's okay. Let's try running it again. Let's see what's happening over here. Whoops, system prompt. I guess I made too many changes. System prompt. Okay, that's now the task description. Okay, third time's a charm. Let's see what's happening. Okay, so now in our debugging logs, we can actually see our complete prompt. Okay, here we go. Answer the following question. Well, look at this. See, I have all of these examples, with the answers. And here. Okay, so it says, I'm sorry, I didn't understand your question. Can you provide more information? Sounds perfectly fine. Let's see. First, let's just make sure it can actually get something right. So let's just look at one of these things that it already knows about. Tell me about how to code swelling of the liver. And I made a mistake. Let's see if it's able to handle it. Go, model, go. All right, ME10, swelling of the liver, also known as hepatomegaly. Sounds bad. Oh, but this was the one that we had in our reference data. Okay, that's great. Let's see what happens if we ask it about a new condition. How to code nearsightedness. Let's make something up. And again, we should be able to see the entire long prompt. And there's the response. So let's see. H42.1, nearsightedness, also known as myopia. So it did follow the format. So we got a code and we got a description. This description is plausible. Now, I'm not sure if this code is correct. We may not expect this code to be correct because, in this application, this model hasn't probably read the ICD11 standard. It may be mixing up different standards. Um, so in the next section, let's look a little bit deeper into how to make sure that it has access to all the right information so they could get the codes right in addition to, having a description, which, actually seems like it's a format that makes sense, providing extra context about the condition that we specified here. I've been generating data just using this ICD11 website and this browser. I also played around a little bit with this coding tool, but now that I want to add a lot more data to the language model, I think it's a good idea to try to download a lot of this data so that we can format it and we can add it to the language model. So let's get started with the API. Here we go. So I was able to figure out that this thing needs an API key. So I had to log in and get an API key. I already did that. That was pretty straightforward. So now we got to get all this data. ICD is a pretty big standard. It has ballpark of 70,000 entries in it for the MMS subsection of the standard. So there's a lot of stuff going on in here. And how do we actually, get access to this? Usually in an application at this point, you're going to want to build a data pipeline. You're going to have to get the data in one format. Maybe it's a bunch of PDF documents, maybe it's a relational database, maybe it's a data lake. In this case, there's an API that has access to it. So we're going to try and get all this data. Let's do that. So thankfully, ICD provides this REST API that we can use. So we already looked at authentication. I was able to get a token. So we can look at the different endpoints that we've got on here. Got headers. Let's just look at the API reference. Okay, here we go. So I don't really want ICD11. I want a linearization. I want to use the MMS linearization. That's probably the most popular one. Could pick a particular release. And looks like we could just call get on this thing and get some essentially we're getting entities. So entities are um, the basic unit of information in ICD. So we just get the entities, and then that returns information about them. They're also organized hierarchically, kind of as we saw previously out here in this browser. There's the root, and then I can go into, oh, 7 sleep-wake disorders, and there's all sorts of sleep-wake disorders, insomnia disorders. And then I can navigate down the tree of entities to figure out, oh, this is the code for chronic insomnia. Um, and, I can add these like severity codes. Um, and, they have ancestors. Oh, look, it has ancestors. So, um, I really think as a good starting point, as in a lot of data engineering kind of workflows is to just download the entire thing. So let's try and just download this thing. All right, let's see where we can start from. So I think they have this API samples, repo, Python samples. I like Python, if it's not obvious already at this point. Let's see. Okay, so this sample looks pretty straightforward. Okay, here's the endpoint. I just gotta put in my credentials in here, and then I can access, particular URI here. We saw, okay, this is the base entity, and then I can just call get on it, and I can like print it and see what happens. So why don't we try doing that? All right, so I have my directory. I'm gonna go into ICD11. And here I have samples. I already downloaded this thing just to see. Um, just as a side note, I'm putting all my keys in here just so you could see a realistic example in this demo. I'm going to revoke all this stuff, before I post this online. So I'm acting a little cavalier with tokens, but that's kind of just want to give you like a realistic view of what's happening. These are just like scripts that I'm playing around with. I'm just going to run this like to download the data, and then I'm going to delete this script or not use this script. So, um, definitely don't do this, what I'm doing here, in a production setting or like in a more realistic setting. I find like a lot of tutorials, they often like block this stuff out, and then you just have no idea like even how to put in the keys if you're trying to do this yourself. So that's why I'm leaving them in here. But yeah, just keep that in mind. Like, you probably don't want to publish your secret keys in GitHub or post them on the internet and so on. Anyways, all of these keys can be revoked, so I'm going to revoke all of these afterwards. All right, so this is the same example that we saw previously, and I've just, experimented around with a bunch of different of these entities. So I can call the base entity, I can call the base entity, maybe we should try this one. I can call the base entity for the 2023 release of the MMS subset of ICD, which is the most popular subset, so why don't we start with that one? And then this is exactly the same thing as their little sample. So we just run their sample. Let's see what happens. All right, it's doing something. It printed it out. All right, I got this whole thing back here. So this was the entity. This is the root entity. So I think it's going to have child entities in here. And it has the URIs for all the child entities. So if I want to, browse the tree of all the entities, I can start from the root, got all the childs, and then I can just start pulling them. Okay, so the first thing that I did is I went through here and I wrote this script to download random entities. Okay, so this is a little bit of a more complex involved script, so let's just kind of walk through this. All right, so because this thing is big, I didn't really have any idea how many entities there were. I thought a good approach could be to just randomly sample entities. And just take a sample. Like this is like a sample of the data. So here, this script has a few parameters. Okay, max entities. How many entities do I want to download? How big is my sample? There are a lot of entities. There might be, thousands or tens of thousands of entities. So if I don't want this to take forever, I like to run this in parallel. So let's do 64 parallel requests. Okay, make a random seed. Start with the root. Okay, so I'm just going to start here with the root entity that we just saw from the previous script. And then just going to loop over, downloading all these entities. Okay. And here's my little downloader. This is parallelized, so this might be a little bit confusing to look at, but basically, what are we doing? While, the number of visited entities is less than the maximum entities, less than 1,000, we're going to keep going, and we're going to draw a random sample. So there's a pool of entities that we've discovered so far by traversing, this like set of entities, and we're just going to pull a random sample, so you get some random URIs. And then I'm going to submit download jobs into a thread pool. So I got a thread pool with 16 threads. And I'm going to call this download entity function on them. And I'm going to, download the entity. And then, just return this thing as an iterator. So this syntax in Python turns this function into a generator. I'm on vacation, so my kids are screaming in the background. Go, little kids. Hopefully you can just tune it out. All right, so these things are coming back from the thread pool, and we're just going to return them as an iterator. So yield in Python, yield entity URI, and the future, this is the result. So it just yields the results. And we can look at what's happening in the actual download script. It's basically the same thing, just copied out of that sample that we got from GitHub. Okay. There's our access token thing that we had to do. Also remember this is just straight out of that sample. .py. All right, so that's it. So this is a script that's just going to download 1,000 random entities from ICD, okay, and save them into a file. So I already ran this thing and it already generated a bunch of stuff, but we can just kind of run it again. Hopefully it's not. We just look at where it's going to download to. Save entities, entities.json lines. That's fine. I saved them already in my best entities here. So let's just run this and see what happens. All right, visiting a whole bunch of them in parallel. You can kind of see it going. It's going pretty fast, not too bad, like, getting up to like 13 entities per second downloading. Okay, so and again, the reason I'm doing this is I want to just download all of this stuff so that I have it all locally. And then that's the starting point of my data pipeline. This is definitely not in the right format that I needed to be in if I want to train a language model on it. But first step, let's just dump all of the data into one place, kind of in a raw format, get all the information in there that I might possibly need. And then later on, we can start processing it and formatting it and building a data pipeline around it so that we can feed this into our language model. Okay, so yeah, again, going pretty fast, and this is taking a random sample of the data. Also, I just know, like, when you're building a language model like this, you might want to take a random sample of your data. You may have a huge amount of data. It may be like pretty hard to cram all of it into the language model, but a random sample is a very common tool that we use in machine learning very frequently when we're just trying to, get a sample out of a distribution of data. So this is, we're trying to, just get, some coverage over all of the different entities that exist in ICD, all of these different diagnosis codes. All right, great. We grabbed about 1,000. So let's look at them. Entities, and they should be pretty random, so they should be kind of all over the place. We did have to traverse the tree a little bit, so the first few are going to be from the top of the tree, but then once we get a bunch more that we've traversed, they should be a little bit more random. Okay, here we go. So what do these entities look like? We can just look at some of the codes in there. Chapter 2. What is this thing? An abnormal cellular proliferation. Neoplasms, that doesn't sound good. Used for condition, okay. Yeah. But then there's also some childs. So we have the entities, we also have the linked information. So, this thing has childs and parents in there. So if we ever wanted to, we should be able to reconstruct the whole tree of entities or graph of entities. But we also have some, basic information, like we have the codes and we have English descriptions of what the codes mean. So, this is a reasonable starting point of like a lot of new information. And, based on what we've seen before, it doesn't seem like this um, model has been trained on this kind of information before. So it's a good starting point for um, for a data set. Okay, so now that we have some data and we can download all the data, I actually downloaded the entire thing. Um, and I put it into this thing, best entities. Okay, so this is the entire thing, just a huge amount of entities. Some of them are better than others or like more well described than others, but there we go. So downloaded all of the MMS 2023 data set from ICD. So now we're set up. Let's move on to the next step where we try to incorporate this information into the language model, and we're going to start by doing it with RAG, retrieval augmented generation. Basically, we're going to build a search engine over this data that I just downloaded. So let's see how to do that next. Now that we have some data that we've downloaded from the ICD website, and we have a base model with a prompt template that's set up, let's add some of that data to our prompt using retrieval augmented generation. Okay, so this is where RAG comes in. If you remember from our prompt engineering example, we had this prompt template. We filled out every section of the prompt template. We filled out the task description, the task parameters, we had some training data. We just don't have any RAG data. So remember, the tension in the prompt design is we're trying to cram as much useful information as possible into the prompt, but we're running up against a size limitation. So we can use RAG to kind of work around this problem. Depending on the query, like depending on what the user is asking about, maybe they're asking about diseases of the skin. Well, it might be more useful to the model if I retrieved example data about diseases of the skin and provided that to the model. So then I could make better use of the limited amount of information, the limited amount of computation that this model is doing. So that's kind of the principle about what's happening with RAG. But um, if we want this to work for a real application, we need some data that we can retrieve. So we saw last time in our ICD directory, let's go back there. Remember, we downloaded some entities, all the entities from the ICD11 standard. But these entities are a little bit complicated looking. They're just JSON objects. They have a bunch of URLs in them. One of the mistakes that I see people make when they're using RAG is like they just export a giant CSV file, or in this case, giant JSON lines file. They basically dump their entire database, in this case, it's a graph database, dump the entire graph database into a file and feed that into a RAG library and expect that to have good results. Well, there's a lot of garbage in here, and that's going to be confusing for the model. Maybe the model can extract some useful information out of this stuff, but also there's a lot of garbage. So let's do a little bit of data cleaning and data processing and data formatting to get this into a format that's a little bit better. In this situation, this particular example, we're kind of lucky because each of these entries, each of these JSON objects in this JSON lines file corresponds to an entity. It's almost like a dictionary page or like a page in an encyclopedia in ICD. So it's a very natural unit to break the data up into. So a lot of other problems, you may just have like a pile of PDF documents or some Wikipedia pages, Confluence pages that you have floating around. And so they might not be broken up into these like very natural chunks of information. And so you may have to spend some more effort like processing it, but at least here, even though there's a ton of extra information like the links or, maybe some metadata in here that we may not want, at least the data is broken up into meaningful chunks. So we can start from that. Okay, so I wrote this additional script here, generate descriptions. Let's generate descriptions. What does this do? All right, so we already have all of our best entities. I compressed it, gzip compressed it. It's kind of big, like 50 megabytes. Not actually that big, right? Totally fine to just store the entire thing on this laptop. I'm running this on a laptop. if it's not already obvious. Totally fine. Um, let's see. So what am I doing? Just open the gzip file, read line by line, pull an entry out one at a time. And so that's giving me my set of entries. Next, I want to generate what I'm going to call descriptions. Descriptions are going to be these chunks of text that are more like a prompt, that's more like in a better format, that's better for RAG to work on, and also better for the language model to work on. So what am I going to put in there? Well, I read through the data and I found that, you know, entries or entities often have codes in them. If they have like the actual ICD code in them, diagnosis code in them that I want for that entity, this is probably a very relevant piece of information, so I want to include that. So I'm going to add that to my description. Some of them often have a title and a definition or a long definition. So there's just extra English textual description of what this code means, what this entity means. So if it's available, I'm going to put that, together into a description. Then I'm just going to add that onto the entity and save the whole thing back into a best entities with descriptions file. Okay, so this script really simple, does almost nothing, but it takes a few sections, few like piece of relevant information from those like giant JSON objects, and then puts them into like a single string that describes each entity. So that's a starting point. Let's start with that. See what happens. Generate descriptions. Okay, running. That ran. It wasn't too slow. It was pretty fast. So now we got best entities with descriptions. I already ran this once, I already decompressed it. So here it is. So let's look at it. This is also still going to be uh, in JSON lines format, right? So if I just open this thing, it still has even more, random garbage in it, but it has a descriptions field. So let's look at that descriptions field. Let's cat it with descriptions, put it into JQ, pull out the descriptions field, and put that into less so we can, I didn't do that. It's called description. All right. So we can look at this thing. All right, the first entity, title, the whole title of the entire thing, ICD11 for mortality and morbidity statistics. Great. Code 10 is a chapter, diseases of the ear or mastoid process. Great. Let's scroll down and see what some of these other things look like. All right. GBO3, atrophy of the testes. Wow, that sounds really terrible. Hope that never happens to anybody, but I guess if it's in here, it does. Whoa, okay. Guess I just picked a random one. Yeah, that's the wonderful thing about working with medical information. This is why I think it's hard for me personally to be a doctor, just as an aside, because man, oh man, um, dealing with people on like the worst day of their lives. I think it's really important. Go doctors. I love you. We need you. But man, oh man, that's rough. Okay, this one is maybe not so bad. NC50 injury to the fingernail. I think that's happened to me before, probably. Maybe not so bad. But all right. These things make sense, right? Like imagine that I was trying to answer a question and maybe I was interested in like something about the small intestine and I retrieved this entity right here. That would be helpful. Or imagine like the model knew about this kind of knowledge, like it knew code DA92 meant other acquired anatomical alterations of the small intestine. Probably I could do a little bit better with these entities. Like maybe I could add in some like parent-child information. There's a lot of linking information. This is like a graph database. So I could have probably added that, but let's just start with this as a first step and we can see what happens. Okay, so I have that information. Okay, so this is a starting point of basically chunks of data that I could think about retrieving and inserting them into my prompt. So let's go back to the tutorial. Let's go back to our tutorial. We've already done playground prompt engineering. Let's go into RAG. Let's look at the RAG tutorial. Okay, so we've got some data that we can load, but how does RAG work? I feel like a lot of RAG implementations, they really wrap it all up in a black box. And we have a black box too. Okay, you can import retrieval augmented runner and you can load some data and then you can call it. Great. And it hides all of the details of what's happening. But RAG is actually very simple. So we can also open up the black box and we can look inside and we can see how every single step of this is working. And that's kind of what I want to walk you through here because it's not that complicated. And if this thing breaks, like if it doesn't do the right thing, you probably want to open up the box so that you can fix it. Um, okay, so let's just go through, a quick explanation of like how does this thing actually work? All right, how does it work? Let's say I have a user prompt. Um, and we saw some of my prompts before, like how do I code nearsightedness? Okay, so we're going to scan through all of our data, right? Here's our data. Scan through all of this stuff, and we want to find relevant information in here about nearsightedness. Now, this may not work, right? Like it may be hard to figure out exactly what are the most relevant things here. They might use like complicated medical terminology. It may not use the word nearsightedness. So how are we going to do this? Um, it's basically a search algorithm, right? We're running search. It's like imagine you're Google. You're trying to find a needle in the haystack. You're trying to find the right piece of data, the right website out of a big pile of data. So here's our big pile of data. Um, but we'll talk a little bit about exactly how that works. But just say like imagine that's using search, that's using retrieval. There's a retrieval algorithm that's running to do that. All right, now we got the relevant information. Um, you already know what a prompt is. You already know that a prompt has different sections in it. And we're basically pasting that information. We're pasting these entries into the prompt. So the model has access to it. It's like, oh, here you go, model. The definition of, let's just say I was looking for something that was related to hypersensitivity. So here, code 4A8Z is allergic or hypersensitivity conditions. Great. That would be relevant information to have if I'm trying to figure out how to code for hypersensitivity. Okay, so that information gets inserted into the prompt. And then finally, we just run the model. It's just running a language model at the end. Okay, so um, there's a number of, because like there's a number of steps that are going on here, I actually feel like I want to draw this with a diagram. So let's open up a diagram, and I apologize for, making it really just difficult to draw in Google or something like this. But let's see what we can do. All right. So we had all of our data, right? We had like a giant list of these entities, right? ICD entities. Okay. How is RAG going to work? So first, we're going to take these entities and we're going to run them through a language model. Okay, so let's just say here we have a LLM, and this is a very particular type of LLM. Okay, so this is an LLM that is not going to be text in, text out like our Mistral model. This is a different LLM that's optimized to generate what are called a vector embedding. Okay, so this is called an embedding LLM. Okay, LLM that generates embeddings. Okay, so we have all of our data, all of these entities, and they're going to get run through this embedding LLM. And then they're going to produce a vector embedding. So we're going to produce a bunch of vector embeddings. I'm just going to draw one. Okay, what is a vector embedding? It's just a list of floating point numbers. I'm just going to make up some floating point numbers. Okay, big list of floating point numbers. One, vector of floating point numbers for each one of these things. You think of this like, what is a vector embedding? If you've never seen this before, read the Word2Vec paper. Just run one best paper at NeurIPS. But sorry, more seriously, it's just a representation of whatever that text is. It has all of the information. The idea is that it has all of the information that, like all the semantic information, all like the textual information, all the content, the facts, everything is just encoded in these floating point numbers. And vector embeddings for text like this, they should obey properties of vector spaces. So this is based on a concept that's called the vector space model. So it just means that like operations on vectors should make sense when they're applied to these vectors. The most common operation that I'm going to use on vectors here is going to be a distance operation. So like a similarity operation, like, oh, this is a vector. It represents some point in some highly multidimensional space. And points that are nearby this point are more similar to this vector than points that are far away in the vector space. Okay, so what does that mean? It means that from a similarity perspective, text, whose vectors are close in the embedding space are more similar. If I have the exact same thing, I just modify like a few words in it, it should have basically the same vector embedding. If I use different words to describe the same thing, they should be pretty close in the vector embedding space. Similar concepts like king and queen should be pretty close, in the vector embedding space. Um, Okay, so that's kind of the point of the vector embedding and like what we're doing. You can use all sorts of different models for this, and when we're talking about this, I should probably just note like how you even know which model to use for this. I previously just talked about like, okay, we're using Mistral. That's a pretty good at this point, like LLM. Um, for generating text, what's a good LLM for embeddings? Well, like everything else, there's a leaderboard in machine learning. So there's this massive, what is it called? MTEB, there we go, search history. MTEB leaderboard, massive text embedding benchmark leaderboard. Um, let's take a look at this thing, and has all sorts of models. One of them is fine-tuned on Mistral, which this thing changes all the time, so you can pick your favorite model here. There may be some trade-offs here. Actually, one thing I want to note about this, like while we're on the section of this LLM, and we're producing this embedding, just remember this LLM is expensive, right? Running an LLM is expensive. If you run a giant LLM that has 7 billion parameters, that means for every single token in the input here, you're doing 7 billion, actually 14 billion, you're doing 14 billion floating point operations. Just imagine like how computationally intensive that is, right? Like imagine like a parser or something, right? I might be like doing a few instructions per character that I'm loading or like token that I'm loading. A language model is doing 14 billion operations per token, right, in this input string. So huge amount of computation. And it gets bigger, right? The bigger your model, the more computation you're doing. If you're running a 7 billion parameter model, you're doing 10 times less computation than a 70 billion parameter model. So this thing, like where I'm actually running this thing through here, is enormously computationally expensive, and it gets more expensive if you use a larger language model. So one of the trade-offs that you always have when you're picking a language model is, well, maybe some of the models, maybe at the top of this leaderboard, are pretty accurate, but hey, 7 billion parameter language model, maybe that's really expensive to be running on a enormous, data set. If I have like 100 million entries, right? It might be like super expensive to do that. So I might want to go down and pick one of these like smaller models. Oh, look, this one is only 100 million parameters, right? That should be ballpark of 70 times faster, than the one all the way up at the top here. Um, okay, so hopefully that makes sense of like how you'd pick a model to use for this vector embedding. So, all right. Um, we made a little bit of progress through this. Okay, we loaded all of our ICD entities. We converted them into text. The text is getting run through a language model. We're producing these vector embeddings. What are we doing with these vector embeddings? Like, how does this even work, right? I eventually want to search for the most relevant ones, but how does that even work? Okay, so let's say I ran this over the entire data set. And let's just say, as a starting point for simplicity, I just pack these things into an array. All right. Okay, here we go. Starting to become like a little bit of a longer, it was already a vector, but now it's becoming a 2D matrix, right? Like one dimension represents different entities, and then the other dimension represents the vectors, the floating point values that compose the vector embedding. Okay, so that's what I got in here. And then um, what next? So next, I'm going to basically have a query. Like let's just say I have my question. right? And my question, how do I code nearsightedness? Great question. Let's see what we can do. Okay, how does this work? I have another, basically the same, embedding LLM. I run this thing through here. Okay, what do I get out of this? Another vector embedding. It's gonna be different. I don't know. I'm just gonna change some of these things arbitrarily because you get the idea. It's different. So now I have a vector embedding representing my query. I have a vector embedding, giant array of vector embeddings representing, all of my data. Um, and I'll also just note, like, if I had a ton of data, I had to run it through an LLM. So like computing all this stuff was pretty expensive. But let's say I did this offline, right? Let's say I built this. This is typically called an index. Okay, index. Let's say I built this index offline, or I ran it as like a batch job or something. Okay, I built the index. Now I have my embedding. How does this work? Basically, I just do a comparison operation. So the comparison operation is basically like I'm, doing a vector dot product. I'm multiplying this vector by, each and every one of these other vectors. And it's not exactly that, I might be doing cosine distance, I might be doing L2 distance, I might be doing some different distance metric, but for all those distance metrics, the work, like the computational work of that operation is a vector dot product. Okay. So I did the vector dot product. That's going to give me a number. That's a distance. So let's say the distance between this one and this one is 0.2. The distance between this one and this one is 0.5. The distance between this one and this one is 2. Well, the lowest distance one is this one, right? Out of all of those. So I do the dot products and then I do a comparison operation. Just pick the lowest one or pick the top 5 or something like that. There's some way of like I get a set of like nearby close examples, and I pick those. So those are the ones that are similar in the embedding space. If this is a good embedding space, then the similar ones should be most relevant, closest, so on. So what do I do with that? So I found a match. Now I need to take this thing and I need to, let's say this one was the match. I'm going to take that one and I'm going to start inserting this in my prompt. All right, so I have my complete prompt. And remember that the complete prompt had multiple sections in it, right? So it had the Google task description. It had task parameters. It had training data, few shot data, and it had a section for RAG data. And finally, it had the query itself. Okay, so what happens? This one that was retrieved, let's just say the first one was retrieved just to make my figure easier. It goes right there. Just paste it in there into the prompt. And then how do I complete this request? Well, I have a different LLM. Let's just say this is my normal LLM. I'm going to say for the context of this example, here's my Mistral LLM. Take this one, take this whole prompt, throw it in here, and I get a response. I'm just going to call this an answer, and then I can return the answer to the user. And that is how RAG works. So maybe we can make this figure just a little bit more explicit. Okay, it's like an all-to-all comparison. So if you understood this, you understood all of RAG. And hopefully that wasn't too complicated. So the code for this also is pretty straightforward. I'd say There's a few pieces here that are basically like design questions or design issues. Like one issue is, well, what goes into these entities, right? What text goes in here? You saw that we created like a simple script to do this. That's one thing you could do. You can get more creative with this. We may actually end up editing this. You may chunk it differently, break into units of different sizes. You may include different information in it. You may change the way that the English text is like actually put in here. You may use a different model here, right? I showed that there's a leaderboard, there's a trade-off, of which model you pick. Also just note a couple like design principles of this. Like in the past, like if we were doing a vector embedding search of like, let's say 5 years ago or 10 years ago, we would have actually used a different technology here. So instead of using an LLM embedding, like off of this leaderboard, we would have used a different method, probably a like methods derived from like a word to vec or fast text. These are just different, vector embeddings. The main thing to note, like what's the difference between the two? Okay, of like, word to vec embeddings versus LLM embeddings. Well, word to vec is super cheap. Like loading this text file from disk is probably more expensive than computing the word to vec embedding for it. Word vec is super cheap, but an LLM is really expensive, 7 or 14 or 70 or like 100 billion operations, billion floating point operations per token. So if these are big chunks, can be like a huge amount of computation. Like this might, even on a GPU that might be running at like 100 teraflops or something, this might take you like a few seconds, right? If you have a data set with millions of entries in there, like we've seen examples of like, oh, this takes on one GPU, churning through all of that, generating like high quality LLM embeddings for all of that stuff might take like a month, might take 10 months, right? It's a huge amount of computation that goes into this. Um, in the past, we used to stress out a lot about this section over here, the index, um, because you would end up with, you might have a lot of entries in this index, right? You might have a million, 10 million, you might have a billion entries in this index. And scanning through this index might be kind of expensive, right? Like this is something, remember, I'm like, okay, I have this thing that's getting generated per query. Look up into this index. Scanning through this thing, if there's a billion entries in it, might be kind of expensive. But it's all relative. So expensive compared to what? It is expensive if your response time limit is like 50 milliseconds. It is expensive, like scanning through millions of vectors. But compared to computing like vector embeddings, not even close, right? Like look at this operation, right? This is an operation that's a dot product over, maybe 100 floating point numbers. So how many flops is that? It's 200 flops. So order of 200 versus this thing on generating exactly the same value, touching the same value, 7 billion, 14 billion. So 10 billion versus 100 is almost a factor of a billion. It's a billion times more expensive to run this thing than it is to, do this like, dot product operation, this kind of like lookup operation. So, um, just one thing that's like a practical thing to keep in mind when you're working with these systems is like, you need to think about how you're going to get the data into this. Um, and then if you're able to get the data into this, like, okay, I did that. Well, for my example, I like encode the entire thing into an index. How long is it going to take to load that index? In my case, I had, 50,000 elements or 70,000 elements. Storing 50,000 elements in a file is not too bad, right? That doesn't take up that much space. Loading, like a few like megabytes of data doesn't take very long on any kind of computer at all. So, um, the thing that we'll probably see, and we'll actually see this when we run this, is like this kind of operation is like a lot more expensive than this operation. And there's all sorts of like optimizations, I guess, that you can do on both sides. There's a lot of technology developed around like how to, okay, here I'm being kind of naive, right? I'm doing this like all to all comparison. You don't have to do an all to all comparison. There are much more efficient algorithms that are like log n or like hash table kind of like constant time algorithms for doing these lookups with some approximation. They're usually called approximate nearest neighbor algorithms. They can do this thing way faster for like much bigger sizes. But I'll just note, like, as a practical thing of like when you're doing RAG on LLMs, this part over here is the computationally expensive part usually. And you might have to have like an enormous amount of data before this index gets big enough that it gets computationally intensive, and you may have to like, in order to build an index that was stressing the limits of any kind of system at all, that you had to reach for one of these more advanced methods, you would have had to have a lot of machines generating all of those embeddings to begin with. So we won't run into any of those problems like this in this example. I'm just going to use the most straightforward, most naive possible way of doing this, because it just doesn't matter. Like, the data set size is not big enough that it stresses like this part over here at all. Um, but just remember, if you did run into something that was a lot bigger and had a lot more data, there's more advanced methods that you could reach for. I'll mention it when we come across them. Okay, so hopefully that gives you an idea conceptually how RAG works. Now let's go and walk through some code. Okay, let's go back to the tutorial and walk through some code. So we know the phases, we know the conceptual diagram. So first thing is prepare the data, break it into chunks. We already did that, in a custom way for, uh, for the ICD dataset. This is what it looks like. Each line here is one of our chunks, right? That's a chunk, that's a chunk, that's a chunk. Okay, we already did that. Broke the data into chunks. Okay, this code here that's in the repo just shows, like, oh, if your data isn't already broken into chunks, like if it's just a giant pile of text files, well, why not just load all the text files and concatenate them into a giant string? Just break up the string into chunks, maybe have some overlap, like a step size, so that when we're retrieving things, we don't have like chunk boundary problems. It's kind of like a filter, running over the entire string. Don't make the step size too big. Make the step size small so that you could have like a very precise hit of, like, exactly where you want it to be. Um, but I just want to note, like, this code does not need to be complicated, right? Okay, right? Chunks. I'm just looping through all of the data and just breaking it into chunks. Loading all of the files in a directory, right, is like 1, 2, 3, 4 lines of code in Python. Breaking it into chunks is 4 lines of code. This just groups it into batches. Batches is a performance optimization. So like, if we, in this step here, if we can like submit a ton of these all at once against the LLM, like running on a GPU, it's just going to be higher throughput because a GPU is very parallel. So one of the themes we'll see here in a lot of places is batching. Well, group those chunks into batches, another 10-ish lines of code. Um, okay. So, okay, I think we covered most of the things in here. I want to actually start looking through code now. All right, great. Got the entities. I've already copied them over here into our RAG section. Okay, so also just in our kind of conceptual diagram of what's happening, this first step is usually done separately. Okay, building this index, taking all of our data, running it through this embedding LLM, building in this index. This is typically done as a separate step from running this query. And of course, makes sense. You want the index to be ready to go when we're running the language model. We don't want to like compute this on the fly for every single query. It would be too expensive. All right, so let's just look through exactly how this works. Okay, so like always, I like Dockerizing everything. If you don't want to Dockerize everything, all the source code is still here. All right, let's start with the top level. Okay, it's called build index. Load that file that I just created. Okay, my data loader is a little bit different, but it's pretty simple. Okay, here we go. All we're doing is just opening the file, reading all the JSON objects, appending the description. Remember, there's a bunch of junk in there. I'm throwing away all the junk and just keeping the description. And batching it up into 128 chunks or entities at a time. And then I have this Lamini index, and I'm building this custom loader. I wrote a custom loader, and the loader is just returning batches of chunks of strings, and that's going to compute an index, and then I'm going to save the index to a file. So this thing probably looks like a black box. You know conceptually what's happening, so let's look at the code inside of it to see what that code looks like. All right, so you have a loader. It's great. When you supply a loader, we're going to build an index. So let's just look at the build index. Okay, there's two things that are going on in the index. One thing is this, the index. And then the other thing is basically back pointers. You know, I kind of glossed over this a little bit when I was talking about this here. I do a dot product here. And let's say this one is the one. This is the closest match. Well, I don't really care about this vector. I want to get the string. I want to get this entry, right? This line here. I want to get this entry so I can insert it here in the prompt. Well, I need to know which vector corresponds to which string, so I need a back pointer. So that's kind of what this thing is here. Splits. It's just the list of all of these strings. Okay, so index 0 here corresponds to index 0 in the list of splits. Okay, so that's what this is. All right, so now I'm just gonna, how do I build the index? Iterate over the loader. Get a batch of text. All right, let's get the embeddings. How do we get the embeddings? Well, Lamini has a library for embeddings. So it's just from Lamini API embedding, import embedding. You can call different embedding models. It's also running, you know, on the cluster that we manage. So this thing's got hundreds of GPUs. If you want to throw a huge amount of data at hundreds of GPUs, just do this. Okay? We've already batched it, so we're submitting 128 requests at a time, right? If you ran this like one by one, it would be like god awfully slow. So definitely don't do that. We're working with bigger data sets now, so we want to submit batches at a time. But it's pretty simple. Okay, instantiate the embedding. We're just gonna use a default model. We tried our best to go through this leaderboard and like pick out good performing models that are a good trade-off of like size, you know, versus accuracy. And we update it periodically. So I'm just going to use the default here. I'm just not going to touch the default. You know, no, you can change that. Like, feel free to use a different model if you want. All right, we have all of our examples. This is just a list of strings. Okay, so we're going to call embedding generate. Now we've got floating point values, right? So now this is, I think there's a bunch of stuff that comes out of here, so we're just going to pull out first element here, which is the vector embedding itself. And we're going to create a 2D matrix. So now we're going to convert this into NumPy. And the reason why we're going to use the NumPy, it's going to come out right here, is going to become a little bit clearer in a second because we use this library that's called FAISS. This is a Facebook similarity search library that uses GPUs. It's just a very well optimized similarity search library. So, you know, feel free to use whatever you want here. You know, I actually feel like in this example, I'm just going to keep to being something like super simple, right? I like this library because it's super simple. It's very highly optimized on GPUs, and it is installable with pip install. So it's very simple. Um, Feel free to use any other library you want here. Feel free to just write this into like a NumPy array, right? NumPy array. Just write this into a NumPy array. Computing a distance metric on a NumPy array is like 2 lines of code. You know, I'm using this library just because I like it, but feel free to use whatever you want here. You know, again, what's happening under the hood is we're just writing these vectors into a NumPy 2D matrix, and we're going to save the matrix. All right, so we're going to add it. We computed a batch. Just basically append these onto the end of the matrix. Also, append the strings themselves onto this array of strings. So you've got all that. We have finished the implementation of build index. That was it. Okay. Now, the only last thing is we're going to save it, and we just save these two things. All right, index, FAISS, that's our embedding matrix, and splits.json. Just save it as a JSON file. No optimization at all happening here. Okay, we save it. You kind of understand what's happening here, hopefully. All right, now we've got this program, build index. Let's try running it. So, like all of these other examples, I like running things in Docker just because it makes the environment clean. But, there's nothing really complicated going here. Mount the data directory, mount the models directory, Docker file based on Python, copy our source code. There's only two source files in here. We saw them both, build index, Lamini index, run, build the container so we get the most recent updated source code, start the container, Python on build index. Don't want to do any of this, just call Python build index. Let's do it. Dockerized rag, build index. All right, here we go. So this is gonna run on the entire data set. Okay, so it's gonna take a while, if this makes sense. I think this thing, when it's doing like these iterations, is doing, let's see, build index, Lamini index, build index. Okay, tk-do. This is our status bar on the loader, so it's pulling batches at a time. How big were our batches? Batches are 128. All right, so we've gone through 14 batches of 128 tokens. So this has taken a while. So this is what I meant of those embeddings, this step here, right? Running all of these like different text chunks through this LLM is expensive. So we're seeing that here. This is taking a while, right? But I'm also making some reasonably good progress. 25 is what? 25 times 128 means we've made it through 3,200 examples. So how long is this going to take? Well, our entire dataset size, I think, is like 35K. So 35K entries that have chunks that have like meaningful text in them, divided by 128 means we got about 270 chunks to go. So if it's been 2.33 seconds per iteration, we got 273 times 2.33, 600 by 60 seconds is 10 minutes. Ugh, 10 minutes for only 35,000 entries. What would happen if I had a billion documents? That would be pretty painful. Um, I might want to run that as like a batch job, like it might take a month. Um, so I'm gonna pause the video here because you probably just don't want to stare at this ticker for a while, and we will resume when it finishes. And we're done. Let's see what happened. Models. We have our index and our splits. Look at our splits. And it is what we thought it was going to be. The index we can't really inspect because it's just a giant binary file. It's just those floating point numbers all concatenated together into a 2D matrix. Okay, so now we've built the index. The final thing is we want to put this together so that we can actually retrieve some data and answer some real questions. Okay, so we're going to go back to our Slack bot. And you'll note here that this is a modified version of the Slack bot. Okay, we're going to use Mistral as the base model for RAG. And we added another function in here. Okay, so when we ask the model a question, we have two models now. Okay, one model is the base model, the one we were using before, and one model is this RAG model. And so what's going on here? So we've changed this a little bit to be ask a question. And here we're adding some additional examples. Okay, we have this new function called getRagExamples. So what's happening here? We created this, basically this rag runner. It's very simple. It's just going to load the index that we just saved from a path. We're going to get some examples. Okay, so the index, we're going to query it. The query it, again, is just doing that similarity search operation. Very straightforward. We're going to pick 5 here. We're going to pick 5 examples. And those are going to be the chunks. So we're going to get out the entities, the ICD entities that we encoded. And then we're just going to do chunk to example. And here, these examples are basically just going to be we didn't fill out the other fields. We're just going to throw the chunk like directly into the context. Okay. So that allows us to reuse basically exactly the same code. It's just when we're adding the examples here, instead of adding only training examples, we're adding training examples plus rag examples. Okay, otherwise the code is exactly the same thing that we had previously. So let's try running it. And just remember, like, that's what our training examples look like. And then we're taking all of our chunks and basically putting them into this format. So let's see, go slackbot, bot up, go slackbot. Token is invalid because I had to reinstall this thing. All right, let's give it a try. Tell me about how to code nearsightedness. Nope, forgot to invite it. Here we go. So let's look a little bit more into this, okay? So first, it's going to ask the base model, which is going to be the model with no rag. Okay. And then, okay, so this is the model with no rag. And then we're going to see what happens next. All right. It actually has a code in here. And let's see what it actually got in here. Okay, so tell me about how to code nearsightedness. And look at that, it actually pulled the correct entity. Okay, ND 90.7, near vision impairment. Near vision impairment refers to ability to perform tasks requiring detailed vision at close distance. So that was an example where RAG worked really well, right? This was something that was very close. We also got some related codes, right? We're sort of gotten 5 in here, okay? Impairment of visual acuity, impairment of uncorrected visual acuity, seeing and related functions. Oh, look, we have an entire table in this. Vision impairment, including blindness. Okay, so you have like an entire table of what does it actually mean? Mild vision impairment, moderate, severe, blindness. Okay, so very relevant information was retrieved. So that means that our embeddings worked and, near vision impairment worked. Okay, now I want to show a different example. So now I want to show a different example. So let's try the same thing, but let's just ask in a different way. Tell me more about code 90, 90.7. Should be pretty straightforward, right? We just saw that it was able to retrieve that. So let's see what happens. Base model, not expecting much out of the base model. Base model doesn't have access to the relevant information that we need here. So let's see what happens. Okay. Look at this. What happened in the next one? Okay. So here we go. It's used to classify vision impairment due to cataract. Is that right? Mild vision impairment, severe vision impairment. Okay, so you got some vision impairments, right? Like 9D and like 9D0. But why didn't we get like 9D0.7? Like that's pretty surprising. Got 9D0.1. We got some related things, but like why didn't we get the most direct one? That's kind of weird. Like if we went up in the lines, right? Um, like to the previous query, tell me about nearsightedness, right? It actually retrieved exactly this one. So why didn't it match it directly? Um, like why didn't it give me this one? So in order to understand what's happening here, we have to look like a little bit deeper into like how RAG works. Okay. So remember, let's go back. Let's go back to this diagram, right? We're taking these text chunks and then we're converting them into these vector embeddings. We're breaking the text into tokens and then we're converting them through this language model into these vector embeddings. Now, vector embeddings are computed per token, and then the model kind of squishes it all together into like one embedding for the entire sentence. The problem is that when we do that, it works just fine on things that the model knows about. So the model probably knows about common words, right? It knows about vision, it knows about near, it knows about, probably a lot of the words in here. And the problem that we run into is rare words. So this code in here, right, 9D90.7, is probably a rare word. Like this is probably a word or a token that the model has never seen before. And the problem with these, actually most search algorithms is, well, problem like tokens or words that the model has never seen before end up being out of vocabulary. Like they end up being out of the training distribution. And so the model just doesn't really know anything about them. It gets kind of confused. It just has no idea what this means. And this is a problem in an example like this, where I want to be like very precise with this like very common term. I want to look up 90.7. I really care about this one. Like the search fails on this one. It should just match 90.7. Like if I just did let's just go back into our data, right? Like let's just go back into the raw data, right? I have the data. And then I JQ description less, I just search for it, 99.7. Oh, that worked, right? Just a straight text search for that worked. But my search engine didn't work, right? My vector similarity search didn't work. Um, so what's going on there? So, again, it's basically just out of distribution. Like this word was never in the training data set that this embedding model was trained on, and so it can't match it. It just doesn't understand it. Um, and that's a common problem that you see with RAG. So like there's actually all sorts of problems that you see with RAG of like, well, I'm searching for a needle in a haystack. Sometimes I don't find the right thing. Like sometimes there's a lot of like different data that gets retrieved. Like, how often, like when I go to Google, like Google is probably going to handle this case pretty well, but like but Google's a really well optimized search engine, right? Like when I'm just putting together like a simple RAG application, I don't have like a search engine that's as well optimized as Google. But even Google, right? Like I'm asking for like any particular search query, I might ask like some, I tried one before, like, how do I parse command line arguments, right? there's probably something that tells me exactly how to do this, exactly what I'm looking for here, somewhere, in all of these. What is that? 35 million results. There's probably something that's what I was looking for in there. But what are the odds that like, I just have a search query and I just press like I'm feeling lucky and like the top hit is like the exact thing that I'm looking for. Like realistically, search engines and RAG, because it is a search engine, have error rates and they're not always going to match the right thing. Um, so what do I do about this? Like one thing that you can do is you can go in and now we know what broke, right? We know what didn't work. We know that like this search here, when I'm like looking up this thing in here didn't work. I could go and edit this. Maybe I could like add additional information in here. Maybe I could, like change the like these are the chunks. I could maybe add more information to these chunks to make it more reliable. I could change the way that I do the search, right? Maybe I do like most real retrieval systems are a combination of what are typically called bag of word. Like I'd actually search for this word, like I'm searching this word in this less command, this less tool, right? I'm just searching for it using a regex. I could just search for it in that way. And I could have some results that are, generated from a search like that, and some results that are generated using the embedding. The embedding would be like better at semantic information. Like, what if I got one character off? Well, that doesn't match anymore, but it would still probably work. Like we talk about near site, right? Oh, look, nothing found in here, but that was a case that worked just fine with the vector embedding. So a real search engine is going to combine like multiple of these methods together. I could add in, a better, more optimized search. Um, so yeah, the main point that I just want to demonstrate here is just that we've seen so far exactly how RAG works. Like we've built a RAG implementation, we've run a RAG implementation, we've seen some cases where it works, some cases where it doesn't work. Um, and then because you know about every single component of this, now you could, you're armed with the knowledge where you could go in and try and fix some of these things. I'm going to stop here. I'm not going to try and fix this particular issue. Um, in the RAG implementation, and we're going to kind of move on to some of the later sections in here, and we'll be able to fix it, in some of these later sections. Um, okay, so that was RAG. Now that we've loaded some data and we've been able to set up RAG on that data, next let's look at actually training a language model. But before we do that, we need to cover section 5 of the tutorial here. We're going to go a little bit out of order here because it's important to be able to use structured output in generating data for instruction fine-tuning. So we're going to go a little bit out of order and go straight into this JSON section. Let's see what's here. Okay, so what's the idea here? Remember, language models are text in and text out, normally. But code doesn't really like strings. Software likes types. It likes ints and strings and floats and lists. So when we're going to extract something out of a language model, we typically want it to be in a structured format. So here's an example of how to do that using Lamini. This is actually pretty hard to do with normal language models. You might have to write a custom parser that can be complex, unreliable. You may have to change your parser for every new model. Lamini takes a JSON schema parser and embeds it in the decoding algorithm of the language model so that the language model is only capable of generating text that conforms exactly to a JSON schema. So that lets you specify some types that you want. In this case, you can ask Llama 2, how old are you? And we can ask it to output a JSON object that has an age field, its type integer, and a units field, its type string. And the language model it is guaranteed to generate a JSON object that follows the schema. So we're going to use this in the next section. And let's look a little bit into how that works. So I have just a simple example here. LLM JSON. Let's Basically the same thing, but here I added in something that's more relevant for ICD. What is the ICD11 code for swelling of the liver? Give me the ICD11 code as a string and the explanation as a string. So these are two separate fields, and I don't have to write a parser to get them out, and I could just get out the code directly. So let's see what happens when I try to run this. Like always, I like to run this stuff in Docker. Again, feel free to just run that script. It was super simple, just run it by itself if you want to. Okay, so here we go. I got a JSON object out of the model. The ICD11 code is K70. The explanation is an explanation of swelling of the liver. Okay, it's pretty straightforward. Just remember all you have to do in order to specify the output type is specify this output type field on the bare Lamini base class or any of the runners. If you're calling this from the REST API, there's also an output type field in the REST API. All right, so now you know how to get structured output out of a language model. It's pretty easy. If you're not using Lamini for this, it's going to be pretty rough. You're going to have to write a parser, basically write a parser that converts the string that comes out of the language model into some format that you desire, or implement one of these decoder algorithms. And I would strongly recommend not doing that. It is one of the most ugly pieces of code that I have seen in years. So there's that. We're going to use this in the next section, so stay tuned. Look at actually fine-tuning our language model. Now that we can generate data, we have RAG set up, we can extract structured data out of the LLM. Let's look at instruction fine-tuning. Let's go into section 4. Okay, so in instruction fine-tuning, we're going to train the language model. We use backprop. We're going to update the weights of the language model. Now, when we're using Lamini, we're typically using an advanced optimization for fine-tuning that's usually called PEFT or LoRa. Think of taking the entire model, which has 7 billion parameters in it, and we're going to freeze most of the parameters. We're not going to update most of the parameters because the model's already learned a lot about English and reasoning and code and just general information you might find on the internet. We don't want the model to forget about all of that stuff, so we're going to freeze most of the weights of the model, and we're just adding in this extra knowledge about the ICD11 standard. So we're going to open up a few of the weights of the model, we're going to backprop through the entire model, but we're only going to update some of the weights, a small fraction, maybe 1% or a little bit less than 1% of the model's weights. And that's what's going to happen here. Now, we're going to do this by training this model on data. So as you saw, when we generated our data, remember, we went back into our ICD11, we generated all of these entities with descriptions, and we ended up with all sorts of data like this is code 4B20.4, ocular sarcoidosis. We'd be able to train the model on information like this so that it learns what the codes are and also learns about these descriptions. Great. So that information, we think of conceptually what we're doing is taking that information, storing it in the weights of the language model so that when we're running the language model, it has access to all of this information. It can retrieve it, can synthesize it together to generate an answer. So that's what we're doing instruction fine-tuning. Now, instruction fine-tuning is a little bit different than normal fine-tuning. We're picking instruction fine-tuning because it's pretty easy. We're building on top of, remember, we're building on top of an existing language model. We're not training a language model from scratch. It would be too computationally intensive to train the language model from scratch. So we're just going to add a little bit of extra information into the language model. So we're doing with instruction fine-tuning. Now, typically when we train a language model, we go through a few different phases. The first phase We train the language model to predict the next token on a whole bunch of data that's downloaded from the internet. Now, this data might include Wikipedia pages, it might include code, it might include Reddit posts. It's just base knowledge that the model learns about. Now, when we train the language model in that way to essentially complete the sentence, it's nice in the sense that we didn't have to process our data at all in order to train the language model on it. So the language model is able to learn a lot of facts, a lot of like useful information, maybe about English, about the world, in this unsupervised way where we didn't have to give it really any kind of instructions other than predict the next word. So it was very easy to train the base language model like that. Didn't have to process all that data on the internet manually. But the problem with the language model like that is that when you start evaluating it, then that model will not really follow instructions. It will just complete the sentence. So if you say the input string to the language model, the input string is what is an apple, it might autocomplete what is an orange because it's just generating a list of questions. Maybe it's seen a bunch of list of questions on the internet. So that's not actually very helpful because we want to be able to ask this model questions. So a further step that usually happens is step 2 when you're training a language model. You take that base language model that's trying to predict the next word, and then you fine tune it on a different type of data. It's usually question answer data, or that's what's called instruction fine tuning. This is the secret sauce in ChatGPT. ChatGPT is really easy to use. It was one of the first models that introduced this at like a public scale that everyone can access. ChatGPT is really easy to use because you could ask it a question and it responds with an answer instead of responding with another question. So instruction fine tuning is the way that we do that. And in order to do that, we train the model on questions and answers, or instructions and then the answer to the instructions, like convert 32 degrees Fahrenheit into Celsius is an instruction. And then the answer, would be the Celsius answer of that. So in order to use instruction fine tuning or to work with a model that's already been instruction fine tuned, we need our data in an instruction format. So that's a question answer format. So that's an important thing. If we don't do that, I mean, you can take a instruction fine-tune model like Mistral and just train it on predict the next word, but then it'll go back into that like answering a question with another question kind of format, and then you'd have to redo the entire instruction fine-tuning process again in order to get it back in there. And so that's just a little bit too complicated, and we don't like to do that. So instead, it's better if we can take our data and put it in a question answer format. So for example, it's just a made up example here. Tell me about a bear. The bear eats honey, right? That's a very plausible answer to telling me about a bear. Okay. Um, so we can often use instruction fine tuning for a few different things. So one thing that we can do um, is we can kind of use it to change maybe the format or the um, um, just the style that the model is answering the questions with. We can also use it to take information like facts and load them into the weights of the language model. So those are the two, kind of think of those as two like use cases for instruction fine tuning. Okay, so now that we know about like the different use cases for instruction fine tuning, why don't we kind of walk through more mechanically, like how do we do instruction fine tuning? So we saw previously, we like to convert our data first into these chunks or like, pieces of information that make sense. These are going to be the basis for our like questions and answers. Okay, so we're going to break the data all up into chunks, and then the model is going to learn from, basically questions and answers related to each chunk. And one of the most common questions that we get when people see this for the first time is they say, well, wait a second. I really want this model to be able to like synthesize information together, like, put together
the different symptoms from like 5 different chunks all across the ICD standard to be able to answer like a, relevant question. How is the model going to do that if it's only trained on like questions and answers that come from individual chunks? And the answer is that just remember the transformer, like the model that we're using, is an associative model. It has attention. Attention is kind of like a memory. It's like a random access memory. So we're taking all of that data, all of those like question and answer data, and we're kind of downloading it or cramming it into the weights all throughout this, giant model with many different attention memories in it. And what that enables the model to do is during inference, it can actually load the relevant pieces of information and synthesize them together through multiple steps of processing in order to put all that information together to give you an answer. And that's what it's doing during training. And That's kind of how, models um, like Mistral, who are kind of trained, in the same way on like individual chunks of information, even though it might have been trained on like, one Reddit post here and a Wikipedia page there, it could actually synthesize the information from all of those different sources together to give you an answer. That's kind of the magic and the generalization power of these models. Um, okay, but back to mechanically, how does this work? Gotta break our data into chunks, and luckily we already did that. Remember, our data was already broken down into these entities, so we've already got it broken into chunks. Okay, next up, we're going to generate questions about these chunks. Okay, so effectively what we're going to do here, and this is why you have to understand prompt engineering before you get to this section, because we're going to heavily use prompt engineering right here. So we're going to ask another language model to read this description and ask questions about this description that can be answered with this description, with the information available in this description. Okay, so we'll look at that in a little bit more detail, like when we actually run a real example. We're also right here, we're going to use this structured output. Okay, typically in order to get some coverage over different possible types of questions that can be answered, we want the language model to generate multiple questions that are different. So we want to instruct the language model to read a chunk, maybe a page from the ICD standard like this one, and then generate some questions about it that are different, that might be asked by different people in different situations. And it turns out that it's much easier for a language model to generate different questions if it can look at the previous question so that it can make sure that the next question is different. So it's helpful if we can, in one query, ask the language model to generate multiple questions. And that's where we're going to use the JSON schema, the structured output of the language model. We're going to say generate question 1, generate question 2, generate question 3. And we don't want to write a parser to parse out, the response of this model. So we're going to use this JSON schema, which is going to force the model to put them into these well-defined units that we can just parse out one by reading the fields of this JSON object. Okay, so step 1, chunk the data. We already did that. Step 2, generate some questions about the chunks. Generate multiple questions about each chunk. Okay. All right. So just looking at some code for generating the chunks. Okay. Step 3. Now we're just going to loop over all of our questions. We have the reference material immediately available. Remember, in RAG, we had to look up the appropriate entity. In this situation, because we're iterating over the entities kind of one at a time, you don't have to look up anything. The answer is found in the entity. If I'm asking a question about code 4B20.4, the answer is right here in the definition of 4B20.4. Okay? We're going to prompt the language model to try and ensure that the answer is answerable, that the question is answerable given this information. We'll look at that in a little bit. We actually run this. But the main point here is that there's no opportunity for the language model to fail, the search to fail. the search to get the wrong page, the search to like find the wrong entry, because we're kind of focusing it on one entry at a time. There's no possibility for it to look up the wrong entry. Okay, so that improves the accuracy. All right, then we're going to generate answers. And then that's really it. We just save the whole thing into a data set, and then we're going to train the model on it. We'll see exactly how that works in a second. Okay, so that conceptually is the process that we're going to go through for instruction fine-tuning, and also a little bit of background about how and why we do instruction fine-tuning. All right, now that we've talked about it, let's look at the code and see how it works. Now that we know how to do instruction fine-tuning, let's begin by generating our data set. Or you can really think of this as just post-processing our data set or ingesting our data set. You already have the ICD data set. It's just not in an instruction fine-tuning format. So the first thing that we're going to do is we're going to convert it into this QA format. So let's do that. All right, here's a script to do it. Now, it's going to be pretty straightforward. We load our entities. We already saved those entities. We've seen those before. We generate questions. We're going to answer the questions, and we're going to save the questions and answers. There's a few subtleties here. Okay, the two biggest issues that we're going to see here are, well, what are our prompts for question generation, answer generation? That's the first subtlety. The second design issue here is performance. We want to generate a fair amount of data. Usually a rule of thumb is bare minimum 500 questions and answers. You probably want more like 5,000, and the more the better. But as we make this stuff bigger, we're generating all of this data, processing all this data with a language model. This is going to get computationally expensive. We're also training. Training is computationally expensive. So now we're in the realm of things that are computationally expensive. So we need to think a little bit more about performance as we're starting to kind of scale up here than we have before. So this is going to come out in a few places in this code. Okay. So the first part here, load our entities and randomly shuffle them, is not really different than what we've seen before. That's fairly straightforward. You know, this part here, fairly straightforward. Remember, we already had saved these things into your JSON lines file. We're just loading them and randomly shuffling them. That's not too bad. So now let's look into generate questions. Well, one thing immediately we're seeing here is we're introducing batching again. So batching is a common theme. We want to generate a lot of questions at once because GPUs are parallel and they like batches, and especially when we're running this on Lamini, which you think of it as just one big GPU, but it's in fact a cluster of hundreds or thousands of GPUs. And so to keep all those busy, to like take advantage of all those GPUs that we have available, we want to submit a really big batch. And you can see some parameters up here. All right, I'm going to generate 120 questions and answers in a single shot in a batch. You can tune this parameter. This is a performance sensitive parameter. It's a good default, I think, to start out with. And we're going to generate 360 questions, 3 batches. That's just a starting point, just as an example here. You know, feel free to make this thing larger. You probably do want to make this thing larger. Okay. But I'm just going to use this as an example. Okay. Also, you'll note the style of this code is written in a little bit of a strange way, and so I'm going to like try and walk through why that is. Okay, first we're batching it, right? We took a random sample of entities, then we're going to form batches. Batching code is pretty straightforward. It's just, you know, group them together into mostly evenly sized batches. Now, we have this concept of a question generator, and then we're going to be able to iterate over it and yield the questions. So the reason why the style of code here ends up being a little bit strange, you know, it's like, why do we need this generator thing? Why can't we call the model immediately right here? So the whole batching logic and unpacking logic, right? So here we batched it, generating questions. Here we're kind of unpacking individual questions. Basically, what's happening here is there's a rate mismatch. So let's say there's 120 entities that come into this. Well, the question generator is going to generate more than one entity or more than one question per entity. And so there's going to be more than 120 questions that come out of this, like after a single shot. And so that's one reason why we have this kind of wrapped up in a generator. It's kind of handling this like unpacking of the batch as it's coming out of the language model. Um, that's one reason why we have this code is written kind of in this way. And there's another reason why. Um, Basically, you'll kind of see here this entire style of all of this stuff is written as generators. Again, you don't have to do any of this stuff. This is all basically performance optimization. But because we're trying to generate a lot of data, the performance optimizations will significantly reduce the amount of time that you have to spend on this. Um, and then there's one other reason. So one reason is performance, and then the other reason is error handling. So I'm submitting a lot of requests, right? Like let's say max questions here. I'm submitting 36,000 requests. Well, what are the odds that one of these questions, doesn't work? What are the odds that for all of these things, I'm opening up internet connections and I'm communicating with servers that are all like working on running different language models. What are the odds that like I have like a drop packet or like a failed internet connection or something? Like as the amount of data here goes up, the odds of a failure also go up. So for that reason, um, we actually have generators in here. Okay, so we're going to see this. This is all, if you look at the style of this code, this is all essentially lazily generating everything. So that at the very end, they have questions and answers. This is the very end. I just have this list of questions and answers coming out of this. I can fast forward. I can like look at the file, that's already been there, that's already written, where the questions and answers are already written in there. And I can fast forward and skip ahead, for example, if this script crashes, like, oh, and it's also going to take a long time, so I might want to be able to restart it. So I can restart if this thing ever crashes. I don't want to be 20 days into a data generation job and then the whole thing crashes and then I lose all my progress. So I want to be able to restart. So part of it is written in that way. It's written in terms of generators that that lazily compute everything so that you can basically fast forward and restart. It can also do error handling. So here I can basically try to get this question and answer lazily computed right here, handling batching and handling different types of batch sizes and the input batch size different than the output batch size. So handling all of that stuff. Um, I can try running this thing here. If it fails, I can just skip it and move on to the next one without crashing the entire program. And if I want to restart the whole thing and have it recompute everything, I can just rerun it. So that's kind of why the style of this is written in this like a little bit less than straightforward way, but it's actually not too bad. So let's just walk through it and see kind of how that works, kind of more mechanically. All right. We saw batching already. We saw the question generator. Let's look at what happens inside the question generator. Okay. The question generator has an iterator that's going to expand the number of entities that were loaded by a factor of 3. So here we're generating 3 questions per entity. You could change this. And we're yielding this question class, which is a reference back to the generator and the index within the generator of which question it refers to. Okay, so the idea here is the question generator is like a feature, or it's like a object that's going to lazily compute all of the questions, and it's going to spawn off these individual questions that hold references to it. So once the whole batch has been computed, we can kind of pick off the answers. Okay, so when we call get on it, this materializes it. If there's an error, handle the error, propagate the error. If there's no error, well, actually generate the questions. And now let's look at how this works. Okay, so generating the questions. We're going to take the entities and we're going to convert these into a prompt. So let's look at the prompt. You're going to carefully read through a page of the standard and generate 3 questions about it. Okay, the ICD standard. Here's a description about the Mistral runner. Got a batch of prompts. We set our output type, question 1, question 2, question 3. We generate 3 questions. We have a system prompt. You're a medical coding expert who's just read the recent ICD11 standard from the World Health Organization. All right. So we did a little bit of prompt engineering on this. We can generate 3 questions. We're just going to submit this thing as a batch. Okay, there's the batch. And if it succeeded, we're just going to populate our list of questions that our question class objects have references to. Okay, let's look at our question class. Well, it just has a get method on it that's going to fill out the entity that the question came from, the question itself, and it's going to read out of the question generator. And if it hasn't materialized itself yet, it will do it right there. Okay, so this gives us error handling. It gives us lazy evaluation. It handles batching of different sizes. Okay, generating answers is basically the same thing. So now we have an answer generator. We're doing batching again because we can have had to take the batch of 120 questions. Now we're expanding it to 360, right? We have to rebatch back down to 120 because each of our batches that we're submitting is 120. We got another answer generator. Is basically doing the same kind of thing. We just have a different prompt. So you're going to read through a page from the standard, ICD standard, answer a question about it. Here is the page, and now answer the following question using the information from that entity. Okay, same thing, throw it in a, run it as a batch, grab the output. We didn't specify an output type here because there's only one string that we're going to take as an output type. Okay, and that is it. So the logic over here, restart, this thing has crashed. Okay, so we're going to generate a file called questions and answers. All right, let's do it. I don't know what I changed. Did I change anything? Oh, I actually don't want to generate that many. Okay, great. Let's see. Let's run it. Actually, first, before I do this, let me remove any existing data that I had already generated. And let's run it. Like always, I like to run things in Docker. Generate data. Here we go. All right, so this is it just loading all of the entities. Now we're going to generate 360 questions and answers. And that was pretty fast. We got 40 QPS about on here. It's pretty good. So again, we're running batching, so that's why this can be pretty fast. Got it. Let's look at our data, questions and answers. All right, and here, let's just do it with, let's format it so we can read this more easily. Data, questions, answers. We kept the entities around. It's often a good idea just to keep around all of the data that you might need in the future. Question and answer. Let's see what we got. Actually, let's just do this. All right, here we go. Let's look at some of these. What is the definition of Sézary syndrome according to the ICD-11 standard? Sézary syndrome is a type of lymphoma that affects the skin and lymph nodes, characterized by presence of large release red scaly patches on the skin and enlarged lymph nodes. And that's useful. What is location being referred to in the code XA2LG6? It is the deep transverse perennial muscle. Great. Okay, so these look very plausible and they're in a question answer format. So we have just generated an instruction fine-tuning data set that we can use to train and instruction fine-tune our model. Okay, great. Now that we've generated some data, let's run instruction fine-tuning on it. So we have a really simple training script that we're going to use to do this. Okay, here's the script. I'm going to import the Mistral runner. We're going to, for the first time that we're training this model, we're just going to have the data be in a format of question and answer, or instruction and then response. We're not going to include any extra system prompt or do any prompt engineering on it. Prompt engineering is something that you do after instruction fine-tuning. It's not something that you do during instruction fine-tuning. Okay. So we're going to set the system prompt in the runner to a blank string, or we're effectively setting the rest of the prompt to be blank. We're just doing the question answer. Okay, we're loading our data. We already prepared our data. We're going to extract out the question and the answer from the data. And it's important to note that when we're doing the training examples, remember we have to kind of adhere to this prompt template. So if you remember back from our prompt engineering section when we're looking at the Mistral model, we're generating these training examples, and they kind of went start token, instruction, all this stuff, but you know, the question, the important part of this, the question, close the instruction token, provide the answer, and then remember this end of sequence token. So we want to put in these end of sequence tokens here so that when we're training, the model is effectively being trained on, you know, groups of units of instruction, response, or question and answers with exactly the tags in exactly the right places. So we're just being consistent with the existing prompt template that is already there. And if you think of like how the model is being trained, it's just going to generate a huge list of these things. Like imagine tons of examples of these things are going to be concatenated into a giant string, and that is what the model is going to be trained on. Okay, so that's kind of mechanistically what training is doing. And that's why we're adding this end token here. We've already got the prompt template happening. Questions getting inserted in between the instruction tags. The answer is getting inserted after that. And then this end of sequence token is getting inserted after the answer. All right. Remember, just keep in mind what your prompt template is when you're training, as well as in every other use of the model. All right, so we loaded the data. We're going to now load this into the runner. Okay, load the data. The input key is the question, output key is the answer. That's just what we had in our data. And then we can just call train on it. And this is going to submit a training job to our cluster of GPUs, and it's going to get scheduled on one of those GPUs or some of those GPUs, and they're going to train that model, and then it will become available after we've trained it. So let's run this training program. Again, like everything else, I like to use Docker. My Docker script is just going to call that Python script in a clean environment. So let's run, and it runs. And pretty quickly, it starts a job here. And it turns out that I've already trained exactly the same model. So we detect that and we just return it. Normally this would just sit here for a while and then we can go and monitor the status. So why don't I actually do that? I'm going to change the job a little bit. Probably I'm just going to change the data. Let's look at my data, questions and answers. I'm going to delete one out of there. Or let me just change a little bit in one of them. And then let's submit the same thing again. because I want to show you exactly what this looks like. Okay, so it sits here after it's submitted, and it creates this training job. You know, this link, and we can log in, and we can look at this training page, and we can see that the status is in progress, and it was started. If I want to cancel it, I can press the cancel button. I'm not going to do that. There are logs. So this is kind of the raw log that you're getting. And it goes through multiple steps here. It like loads all the data. It loads the model, the base model. So again, we're starting from this Mistral 7 billion instruct as a starting point. It's going to load. I can refresh this log, kind of see what's happening as it's going. I can also go back out to this like main training page, and I can see like a list of all the jobs and different things that I've run. You can submit multiple jobs if you want. There should be plenty of GPUs for you to run jobs on. Do you just want to look at a few things here? I just want to wait a second until it finishes loading. This might take like a minute or so because the model's pretty big. You have to move the model over to the compute node that it's running on. This is just something that happens at the beginning, but I do want to just look at a few things that happen in this log. So let's just wait a minute for that to happen. Okay, while this is happening, I can just mention a few things about training. Again, we're using a technology that's called adapters. So essentially, we're taking an adapter and grafting it on the end of this model. If you're running this yourself, it's fairly like you can set up a training pipeline. You've got to get some GPUs. You've got to, you can set up like a training system. There's all sorts of like training frameworks that you could use. I think it's pretty straightforward just to write a training pipeline on top of Hugging Face. The things that are hard about it are usually distributing it over multiple GPUs and getting good performance out of it. But if you're just interested in playing around with it and maybe like not getting the best possible performance, that's totally fine. You should be able to train on like a modest amount of data, even on like one GPU that that's come out in the last 5 years or so. Um, but if you want to train on a lot of data, you really need a lot of GPUs. That's why training gets expensive. Okay, so the model is loaded. You can kind of see the model architecture, and then we actually enter into the training loop. So here we're going to automatically select a lot of hyperparameters for you, like how long to run the model for. I didn't actually generate that much data, only 300 examples. And so this isn't going to train for very long. It also, as we saw, let's look at that. We have about 32K tokens all concatenated together. They're grouped into batches of 2K tokens, I think. We had 260 training examples. Yeah, again, there's a bunch of hyperparameters. They all change for different models, so you may have to do like hyperparameter search. We try and bake in, good hyperparameters for models that are commonly used, so that you don't have to mess around with that stuff very frequently. So you can refresh again. Okay, so you can see some training information, like, okay, here's a loss. The loss should go down. Okay, so now we're training and it's kind of going. I'm just going to let it go for a while. I'm going to move over into this model, which is basically the same one that I already trained. And we can kind of look to see, how the model is doing. So we have 2 pages in here for basically basic evaluation of the model. And the first page just gives you a side-by-side comparison of what the original model, in this case, this was the original Mistral 7 billion parameter model, would have generated, and then what this model generated. And it also gives you the entire prompt, including the template. So let's see. Let's just look at some of these results. What is the specific anatomical locations of the third or fourth perforated artery? So here it says it's in the neck and the cervical region. Um, and this one says it's in the chest wall. Hmm. Um, let's look at some other ones. Okay, so let's see. What type of cancer is being described in the code ZH1YZ3? This is cribriform sarcoma. And remember from RAG, it was hard for RAG to understand these like codes because these codes are probably out of vocabulary without fine tuning the embeddings. Well, here we're fine tuning the language model. So things that are out of vocab can now become in vocab. So let's see. All right, this thing says the base model has no idea what this is, but let's look at this one. So a type of non-small cell lung cancer. Let's see what it actually is. Google is pretty good at finding these things. Let's see. All right, here we go. Cribriform sarcoma is exactly right. Okay, and carcinoma of the breast. Interesting. Non-small cell lung cancer, breast. Is that right? Has severity NOS. Oh, specific anatomy. Um, is that exactly right? No, this is actually, wait, this is related. This isn't the right page. Look at this. This is not the right page. Coding tool. Didn't work. Um, show ancestors. Let's go back. Okay, specific anatomy. Um, okay, we have severity codes. Let's go back and look at our actual dictionary. Questions and answers. Superform code XH1YZ3 is superform carcinoma. Okay. Okay, and we actually see this one. It is a non-small cell lung cancer. Okay, great. So, let's say this one is right. Um, what is the severity or degree of the injury or condition being coded in XA5TX? It does not. So this one, the base model talks about ICD10 instead of 11, so it doesn't know which one we're in. It says it's related to the femur. This one says it's related to the carpal bone. So let's see what it actually is. Let's try this one more time. Oh, shaft of carpal bone. Okay, great. So main idea is, you know, through fine tuning, because we've fine tuned on this data that's in here, at least the model should, for the data that it's trained on, it should be able to like understand now these facts and this extra information. So now we have a model. The model has a name. We can give it a name. I'm just going to say this ICD11V0. Okay. So this model also has an ID. You've seen probably multiple places in Lamini where we can refer to things by the name or the ID. So, for example, back here in our JSON example, we can say the model name. Well, here I can change the model name to be either this new name that I've given it or this model ID. And I can just start calling this model kind of programmatically, wiring it up to a playground and so on. So we've fine-tuned our first model using instruction fine-tuning. So next up, we're going to go back and look at how to evaluate the quality of the LLM. We saw this a little bit already in the sense that we were able to, compare some results kind of manually of like looking at the results of, all right, this is what our fine-tuned model or our new model produced for this query, and this is what a base model produced. Eventually, this gets tedious to evaluate the model manually. So in the next section, we're going to look at adding some tools where we can introduce quantitative metrics that we can use to determine the quality of the model. And of course, this is difficult in language models because, well, text is really hard to assign a number to. It's different for a classification model, like is this a cat or is this a dog? It's pretty clear, either it's a cat or it's a dog. Either you got it right or you got it wrong. But for a language model that's outputting text, there are a million different ways of explaining the same thing that are all correct. And how do you know which one is better? So we'll look into how to do that next.
How to evaluate the quality of our LLM. So we produced a bunch of LLMs here. We had our initial examples in the playground, the base models. We had models we spent time prompt engineering. We have a RAG model, and we have a fine-tuned model. How do we know which one is better? So eventually we want to start introducing metrics. As I mentioned before, it's really hard to know which answer is better than another answer, because it's really hard to reduce a string, like a complex answer, down to a number of like, how good is this answer? There is a technology that we can use for this though. So the technology comes, it comes out of NLP. It's usually called a mean opinion score. So the way this works is it's based on the idea that there are human experts who are capable of judging the difference between good or bad answers. In this case, for ICD11, probably a coding expert who's been coding medical reports their whole lives is much better at this than I am and would know the difference between something that was correctly coded and something that wasn't correctly coded. And so I could ask a person like that to assign a rating. Usually MOS scores are assigned a rating between 1 and 5. So 1 being a terrible answer and 5 being a great answer. And I could ask them just to assign a score. And I could also compute this statistically. So I could get together a group of really good coding experts, maybe mix some physicians in there, and ask them to rate the answers on a scale of like 1 to 5. And by doing that, I can take the mean, that's where the mean and the opinion score comes from. I could take the mean of all the answers, and then I could average that over a set of different answers. Maybe, a statistical sample. Maybe I could have, 10 or 100 different questions and answers, and I could get, ratings from multiple raters. And so I could compute basically a number, the mean of the opinion score, that score of like a 1 to 5 number, 1 to 5 rating for each of the examples. Um, and then I could get a number to grade essentially how good model A is, the answers produced by model A, versus how good the answers are produced by model B. So that's one way of doing this. Now, of course, the downside of that is I have to convince, a group of, several domain experts to help me out, in scoring my models. And that's kind of expensive and time consuming. There are tools that allow you to do this. You can, for example, use crowdsourcing tools to help you do this. But language models um, give us something that's close to that. So if you can squint your eyes and say, well, an AI like a language model is pretty similar. If I squint my eyes, pretty similar to a human, I could replace the humans with language models in that MOS process. And then I could come up with something like a score that's judging, maybe using a different language model to judge the quality of the output of, just some answers to questions. And um, let's see. So that's kind of the principle behind what we're going to do here. And you may have all sorts of questions of like, how is that even possible, and how can the language model grade itself, when it doesn't even know the answer. Let's look into this. Okay, so let's look into evaluation. Okay, and we're going to use this as an A/B test. So we're going to set this up in a way where we're trying to compare two models to each other. Is model A better than model B? Is model B better than model A? How do we know? Okay, so one thing that we're going to do, just in the same way that we would do this for an MOS test, is we're going to define some set of questions and answers to ask the model. Here, let's just look at the code and this should become more clear. Okay, so we have 3 sets of data that are going into this. And this is going to get us a little bit closer. Okay, so we have a golden input. This should be a correct answer, a very correct answer, something that is factually correct, is informative, is useful. Like if I imagine I had those physicians like rating this, or coding experts rating this, they would give this all 5s. I want a good reference. Okay, so it's very helpful to have essentially a golden test set, or a set of really good, amazingly good answers to these questions. Okay, and I'm going to use this as a standard. And so I'm going to frame the question just a little bit differently. Instead of saying like, is model A better than model B? I'm going to instead frame the question as which model is closer or more like the golden reference? Is it model A or model B? And hopefully that becomes a little bit clearer, that because now I have like a ground truth, like a source of truth, it should be easier for a model that can understand English and can reason and has like basic knowledge to be able to do this comparison. Like even if you're not an expert, you should still be able to know if something is like close or something is like way off, factually, by comparing against a golden reference. So the golden reference is something that helps a lot here. And so it's important and helpful to spend some time to actually put together, some questions and answers that are like absolutely right. And even if you're not a domain expert, like I'm definitely not a domain expert here, I can at least do research. I can at least go and like look up different sources and try and find like references and try and fact check, my answers. And I can build up something through putting in a lot of like work, where the quality of the answers is pretty good. So I tried doing that. So here we go. Gold. It also is nice because I have the reference manual. I have the ICD standard right next to me. Okay, so I can have a question. Tell me about JA40 2.0. Well, it looks like there's a dictionary definition that I can just read out. Intrapartum hemorrhage with a coagulation defect. Okay, so I can just look up the reference. It's like just a straight factual answer. There is a reference for this. I find a reference for this. I can just write this down. So I did this, kind of thing for about 10 different questions, by reading through the standard and trying to pick out some different pieces from the standard. Okay, so these are correct, like in the sense that I verified against the standard manually that these are correct answers. Okay, maybe the formatting isn't great. Maybe they're not as insightful or easy to read as they could be, but at least they're factually correct, which is, a bar that the baseline models couldn't even hit. So these are a starting point for some golden data sets. So let's look at the rest of the script. Okay, got the golden data set. I also have data from model A and model B. Model A here is a base model, so base Mistral, nothing special on Mistral. Model B was our RAG augmented RAG augmented prompt tuned model from section 3 of the tutorial. Okay, and then I'm just going to store the results of this comparison into a file. The script is pretty simple. I'm going to do some batching. I may want to run these comparisons in parallel. It's pretty straightforward. I'll load all the answers, questions and answers, and then I'm going to run the comparison. What is the comparison? Well, this is why we put prompt engineering in the beginning, because we're going to do some more prompt engineering here. Let's create a new Mistral runner. Okay, a new Mistral runner, and we're going to define a new test. The new task is an MOS task, rating task. 2 models. There are going to be 2 models that answer the same question about the WHO ICD11 standard. And your job is to rate them, comparing them to a golden reference. You're an expert rater. Rate the answers using a similarity scale from 1, lowest similarity to highest similarity. Use the full range, read the gold answer carefully, prefer answers that are most similar to the gold answer, even if the gold answer refused to answer the question. Okay? And then here's the question. Here's the golden answer. Model A's answer, Model B's answer. Which model was most similar to the golden answer, A or B? Now, we're also going to use the structured output here. So we're going to ask the language model to output a JSON object, model A similarity, model B similarity as an integer 1 to 5. Okay, so we're going to get numbers out of here. Now, after we've run this thing, we're going to reduce this into a normalized score. So the normalized score is between 0 and 1. 0 means Model A wins. 1 means Model B wins. Okay, 0.5 means it's a tie. Okay, it's helpful. We found it's helpful when we're optimizing something, like in this case, we're optimizing Model B. We're trying to build the best possible Model B. It's helpful to reduce the whole evaluation down to a single number between 0 and 1. So you can also think of it as like a percentage. What percentage of them, of like all the possible points did Model B get? All of the possible competitions did Model B win by the maximum possible amount? So we can try and optimize it. Like as a human, I can go back and try to edit Model B, and if it improves on the score, I'm confident that I'm actually making Model B better. Now I want this metric to be correct. So before I go back and do that, I need to do some validation, make sure that I trust this metric. So one way of adding trust in this metric is adding more statistical power to it. So that's a bigger sample size. If I have more questions, if I have more diverse questions, like a better coverage of more realistic questions, I'm going to have more confidence in this metric. Also, if I agree with this model, right, or if an expert would agree with this model, I'm going to have more confidence in this metric. So I should, while I'm building this evaluation program, I need to actually go and prompt engineer or spot check and make sure that the answers that are being returned by this model make sense. So let's do that. Like everything else, I like to run it Docker. I'm just going to run eval, which is just going to run that A/B test program. Program is pretty straightforward. Okay, I'm going to run it. And it runs pretty fast, and it gives me a score, 0.6875, which means it's higher than 0.5. That means that Model B beats out Model A, which makes sense. But let's just go back and spot check and make sure that this makes sense at all. Okay, so here's a question. What is LD2H.Y? Golden answer. Other specified syndromic genetic deafness, genetic deafness. Okay, model A with the base model. I'm just an AI. I don't have any personal or sensitive information. I can't provide information about this. I don't know what this term is, and I don't really know, but I'll do my best to help. Okay, not that great of an answer. What did the model rate it? It rated it a 1. Okay, model B, LDH.Y is not a valid code. It's possible there's a mistake, so this means like the RAG failed on it, probably. As we've seen it, it's hard for RAG to hit these like specific codes exactly. But it still knows it's a code. It still knows that this is in the context of ICD11, so you know, maybe a little bit of a higher score for Model B. Okay, let's look at some of the other ones. Um, let's see. That one is pretty similar. Let's look at some other ones. Okay, what is the meaning of LD90? LD90. Again, ICD-10 is much more common than ICD-11. Of course, ICD-10 has been the standard that's been around for a long time, so it makes sense that Model 10 would clamp on to the base model would clamp on to ICD-10. All right, so this is the code for diabetes mellitus, which is wrong, but it knows it's a code and it makes an attempt at it. Okay, this was instead conditions with disorders of intellectual development. Okay, let's look at this one. Oh, this one is way better, right? It knows it's ICD-11 and it got issues with disorders of intellectual development. So that was great. Maybe it didn't get this one. No, this is like pretty good. Okay, so let's see what happened. Model B rated 4. Model A rated 3. Okay, I agree with this one, right? Model B should be rated higher than Model A. Um, all right, let's look at this. Okay. Um, let's look at a few more. What is ICD code 20? Developmental anomalies chapter. Failure of a particular body site to develop correctly. Model 1, again, doesn't really have any idea. Model 2, it doesn't really understand that this is a chapter code. And it does note that it's ICD-11. So, Model 1, I would actually rate these like pretty closely. Like maybe, Model B is a little bit better than Model A. I'm not sure if I would do it like by that big of a margin. Um, but again, I don't like completely disagree with that. Let's look at this one. Oh, look, okay, one where Model A is doing better than Model B. Let's see. Okay. What does ICD-11 8A20 mean? Alzheimer's. Okay. This one says, I've got no idea. And what does this one say? This one says other type of cardiac arrhythmia. So I kind of do agree with this one that saying like I don't know is better than saying the wrong thing, like something that's blatantly wrong, right? Cardiac arrhythmia versus Alzheimer's is like blatantly wrong. So this one makes sense to me too. Okay, so overall, I'm not going to go through all of these on the video, but you should actually go through and verify more of them. Um, what did we learn from this? It's possible to rate the outputs of a language model. It's possible to boil it down into a single number. If you boil it down into a single number and you trust the number, then you can make changes to the model. and you can see how that improves the metric, and you have a metric that you can optimize towards. So I can say like more objectively that, model B is better than model A. And if I have a pretty significant margin, I can say, oh, well, maybe it's actually time to release this model. Okay. And if you want, more precision into this, we only had 10 questions in here. If you want more precision, like what's the difference between 0.68 and 0.72? Well, you may just want more examples. I think a good rule of thumb, like a statistical sample is like, ballpark of like 20 or 30 up to 100 might be, give you like individual percent level of granularity. Um, just some guidelines to go by. If you feel like, you can't tell the difference between two models, it's a good sign that, you may want more samples or more questions. Okay, so now we've improved on our base model. We've generated multiple models using different technologies here. We've like built up a kind of a toolbox of different methods that we can use. Let's add one final tool into the toolbox, which is, well, we saw through instruction fine-tuning, how to actually take new data, new information, and embed it into the weights of the language model. Finally, we're going to look at a tool that can help us improve the quality of some of that data. Remember, we just made a first pass over it. Some of those questions and answers might have been a little bit questionable in terms of quality. They still had new information as we looked through, like the model was still able to at least identify codes. So we've added kind of the codes into the vocabulary of the language model. But there were some, issues there. Was that like cancer example, like breast cancer? Was it lung cancer? There was a little bit of ambiguity there. So let's go back and look at the final tool, which is a cool, based on technologies that are called DPO or RLHF, where we can essentially use a powerful classifier or another language model to improve the quality of our training data, which will then further improve the quality of our language model. So let's look at that next. Now that we can train our own language model, let's now learn how to boost its accuracy by including human feedback. The joke about RLHF is that the HF is the most important part, not necessarily the RL. Direct preference optimization by all of these great people goes and provides a lot of experimental evidence for this, that what you really need to do is, well, look, your language model is secretly a reward model. You can use another language model to mimic, just as we've seen, just as we made our A/B test model, to mimic the ratings of expert humans. And we could take that reward signal and feed it back into the model during training. So let's look into how to do that to boost the performance of our language model. Okay, so I'm going to walk through a practical way of implementing this. In Lamini, I'm going to this is going to look like a little bit of a black box when we start out with, like, oh, there's a reward model. What exactly is that doing? I'm going to try and crack open the black box so that you understand every single piece of what's happening here. And this should be pretty simple to implement. So if you want to implement this yourself, go right ahead. All right, let's look at this. So we're going to remember we generated a bunch of questions and answers. Let's start out by rating them by how good they are. Questions with correct answers. These are our high quality questions versus questions that are incorrect. And we're going to use this very high level interface, this Lamini classifier. So I instantiate this classifier. This is like our reward model in DPO or RLHF. This is like our reward model. I'm going to create a reward model here. And the reward model is going to be opinionated about whether our training data, the answers are correct or not, whether they're good questions and answers or not. So here, this is the very simplest high-level interface. Instantiate a classifier. Let's create two classes in the classifier. One is a correct class, one is an incorrect class. Questions with correct answers versus questions with incorrect answers. Prompt train.
It's a very high level interface. We're going to just one shot train this classifier and then save this classifier. Now, at this point, we have a classifier. We could run it on all of our data, and it's going to leverage the power of the underlying LLM as a reward model to grade our answers, very similarly to how we saw the A/B test model kind of grading, which model it thinks is better. Now we're grading individual questions, whether the questions are correct or incorrect. So then you can predict. Here's a question. What is 2 plus 2? Answer. The answer is 3. Maybe I should predict incorrect. Is 2 plus 2 3 or 4? It's 3 is incorrect, 4 is correct. So this is kind of what it looks like programmatically. That's pretty simple. Well, of course, I could train this model with these prompts. Maybe I could, just like I wrote in my A/B test model, I could expand these out to be like better prompts. I could do prompt engineering on either of these prompts, and I could come up with a better model. But I could also add some data, like let's say, what is 2 plus 3? The answer is 5. Oh, that's correct, but the model actually predicts incorrect, just as an example. Well, I could use this interface of calling LLM.add data to class, add to the correct class. 2 plus 3 is 5. In fact, 5. I train the model again, and the model is now able to get the right answer. It's able to know that this question and answer pair is correct. So, again, we're looking at this at a high level. This probably at this point looks kind of like a black box, like what's going on inside of that Lamini classifier. Okay, I'm going to skip over saving the model. Obviously, we could save the model. We could load in more data. Let's look a little bit about how this works using a line-by-line implementation. So I'm going to go through 4 steps. Step 1, data generation. We're going to generate some training data for correct and incorrect questions. Then, we already covered embeddings. We're going to convert that training data into embeddings, vector embeddings. And then we're going to train a supervised learning classifier like logistic regression or BERT on top of those embeddings so that we have a really good way of distinguishing between correct and incorrect answers. And then we're going to calibrate it so that we can use it to, in a very simplistic way, we could use it to like throw out all of the bad examples or, examples that are incorrect, like below a certain threshold. Um, or we could also just use the raw scores. Like we could use those scores to kind of weight the updates that we're making during training as we would in RLHF or DPO so that the model gets more signal from the correct answers and less signal from the incorrect answers according to how confident this reward model is in whether the question is correct or not. Okay, so that's the big picture, but let's look in a little bit more detail into like how each of these steps work. So the most complicated thing here is data generation. So let's look at that. So LLMs are generative AI because they can generate data from a prompt. And we can use this ability to bootstrap a traditional classifier. So there's a 3-step process that goes on to do this. So we take the prompt, here are our prompts, right? Questions with correct answers. And we generate short descriptions of training examples, like very specific, very precise descriptions of training examples. We generate a whole bunch of these like descriptions of training examples. And then we make them more diverse. So we have like the LLM do another pass over the whole thing so that it like looks at, a collection of like 10 examples, maybe examples of incorrect answers. And then it just tries to make them more diverse. So it like covers more of the space of possible incorrect answers. And then finally, we expand them back out to realistic incorrect answers in a final step. So both of all these steps use LLMs. We can kind of look to see how this works. This is the actual loop. There is a example generator, example modifier, example expander. First generate those descriptions
of incorrect examples, then modify them so that they're more diverse and different, and then uh, we add that together with any, with the original ones. So we have the more diverse ones added together with the original ones, and then we generate a batch so that we can generate in batch, and then we expand all of them out into complete examples, in this case of incorrect questions. I'm just using that as a running example. All right, that's it. Generates a bunch of examples. So let's look a little bit deeper into this. Okay, let's look a little bit more into how those examples get generated. So there's a description of the class. So you're a domain expert who is able to generate many different examples given a description. So doing some prompt engineering there. Here's some more prompt engineering training examples. Here are some following examples of real incorrect questions, maybe from labeled data that we had available. We may or may not have that available. So we may or may not have that available. And then read the description of what we're trying to generate of the class, in this case, an incorrect question. And then generate this many examples, be as specific as possible using the most 10 words. Okay. So we use the JSON mode, maybe to generate 5. In this case, we're going to do 5 different examples. Next, once we've got them, we're going to load them all up, shuffle them all together, so they're already somewhat diverse, and then okay, read the following descriptions carefully. Now generate 5 more examples that are similar but substantially different from those that are above. So doing some more prompt engineering in there. And then finally, we're going to expand them out. All right, so we've got the prompt. This is a description of what we want. This would say an incorrect question. Here's an example. Maybe it's a question where, the answer refers to the wrong uses a medical code from the wrong ICD standard. It uses ICD-10 instead of ICD-11. That might be a description. Now expand this into a complete example and be consistent with both the summary and the description. All right, so that generated a bunch of training data. Now we have a bunch of training data. We can have that generator generate as much training data as we want. We're generating data for all the different classes. So it's almost like if you have any data, start with that. If you don't have any data, you have this prompt and you have the LLM like generating a whole bunch of data. So now we're creating a classifier. Okay. At some point while we're going through this, you're probably thinking to yourself, like, why didn't I just ask the language model like a yes or no question? Like, um, you know, is this answer correct or not? Kind of like we did with the previous example. You can do that. Go for it if you want to do that. Um, One issue that you have is like when you say like, oh, is this, if you ask the language model, is this answer correct or not? It might say maybe, you know? So one of the issues is just that like structured output issue of like, you have to parse the output. What do you do if the language model outputs maybe? Or in this situation, yes, but in this other situation, no, it outputs a giant string or something like that. Well, you can use that JSON output and just say, all right, output a bool or output a floating point number, output an integer like we did before in that A/B test. You can absolutely do that. I think the biggest reason why, I kind of like this way that we're showing here in this example is kind of the more powerful way, is that this is going to generate like a loop where it's going to generate a whole bunch of data, which then we can actually go in and kind of like edit and label as a human. And then we can feed that back into our data set and just kind of like keep making it better, kind of like an active learning or like an augmented, data augmented classifier kind of thing. Like this thing is usually more powerful and more accurate. But if you just want something that's quick and dirty, go ahead, call Mistral with the JSON output mode of a bool and just say yes or no. Go for it. That'll be better than random guessing. Um, and then you could totally do that. But this is if you want to go like one step deeper and you want to make it even more accurate, do this. All right, so you've got a bunch of data for incorrect examples and correct examples. Now we need to just build a classifier on top of it. So
what I'm going to describe here is the simplest possible classifier that you could build that's powerful. And you could, of course, do better than this. The reason I'm doing this is because this is pretty much foolproof. Like there are very few ways for this to go wrong. Whereas if you want to do something that's more advanced, like you want to bring out BERT, you want to bring out deep learning, there's a lot of more hyperparameters, there's a lot of more like subtlety and issues. It's not going to be push button anymore, whereas this is pretty push button. So I'm going to stick with this, but just remember that if you want to go even deeper, make this even better, you could probably replace this with a better model. Okay, but I'm going to try and build the best model that I can that's foolproof, where I just push button. Okay, so what am I going to do? I'm still going to use an LLM, but I'm going to use the LLM to generate embeddings. So just like we did with RAG, I'm going to take all of these like examples of fake or synthetically generated correct and incorrect answers, and also real data from like correct and incorrect answers. And I'm going to run it through a language model again in a vector embedding. So I'm going to convert, all my examples into, 1D vectors that represent this chunk of text. So I'm going to end up with a list of floating point numbers for every chunk of text. And now I want to train a classifier that maps from that, vector representation. Hopefully it's a good vector representation, right? It came out of an LLM, so it's using all of the reasoning capabilities of the LLM to generate that vector embedding. But it's a vector embedding. The output is a vector embedding, not a string. Okay. So now I can run it through a training algorithm. Okay, so I can get the labels, class labels, right? Because I know which class it came from. I synthetically generated it for correct and incorrect questions. I could do this for any kind of class. I know what the labels are. So here are the labels. Got the embeddings. So I got Y, I got X. And now I'm in a very standard kind of machine learning setting of X and Y. It's a supervised learning. I know what X is. X is a bunch of vector embeddings. Y are labels. 0, the answer is incorrect. 1, the answer is correct. And here I'm just using logistic regression out of sklearn. I like this one in particular because logistic regression, what is logistic regression? It is the last layer in a neural network. It is like a fully connected layer in a neural network followed by a softmax. That's kind of what logistic regression is. It's the last layer in a neural network. But as a result of being, a consequence of being a last layer in a neural network, it is one of the few problems in machine learning where the optimization of this, like the training, backprop, and then all the optimization applied by that is easy. So this function is pretty much guaranteed to work, and it's going to be very efficient. One of the reasons why I'm not using another kind of model, like, oh, why not use XGBoost or something? Like, you cat boost or something, you can go for it. Logistic regression, because it's dealing with vector embeddings, it is exactly the same thing as the last layer in a neural network. It is tuned, and it's kind of like all of the assumptions that are built into it are based on this idea of I'm putting in vector embeddings into it. So it's pretty compatible and straightforward if I want to use this embedding. And I do want to use this embedding because I'm building on top of the powerful representational capabilities of the LLM. So I kind of want to use this. So that's why, it ends up being these particular choice of models in this example. If you're a machine learning expert and you disagree with this, like, go for it, use your favorite model. Totally fine. I'm sure there would be many good choices here that would work. This is meant to be something that is very straightforward and push button. Okay, so now I've got a classifier. And the classifier is going to be input string, QA pair, output, a score. Which class is it? Is it more likely to be class 1, class 0, which is an incorrect answer? Or is it more likely to be class 1, which is a correct answer? So there we go. But what do you do with the score? So I want to cover calibration a bit because we're going to have to calibrate this thing. What does a score mean? Is point 0.1 good? Is point 0.9 good? Is point 0.5 in the middle? Is it? How do you know? Well, it turns out that we need to do calibration so that we can make decisions using the scores that come out of the model, like we do for any machine learning model. So let's say, for example, that we want to keep the answers that we're 90% confident about. So what would we set the threshold on the score to? So remember, scores are going to, coming out of logistic regression, are going to be normalized between 0 and 1. Okay. So if we just remember, and then the intuition is if we increase the threshold, it's like imposing a higher bar on the samples, right? The samples have to be more likely to be correct, to be selected if the threshold is higher. You know, if my threshold is zero point 0.1, I might have a very wide filter. I might like not actually throw away very much. But if my threshold is zero point 0.9, I might throw away most of my data. But then how do we quantify this? Like what exactly should we set it to? I personally like using this tool of a precision recall curve. So this curve just simply plots precision versus recall at different thresholds so that we know what the trade-off that we're making is at different thresholds. So precision is how many correct answers the model predicted. Like, for example, if we wanted 90% of the answers selected by our model to be correct, we should target a precision of 90%. It's pretty straightforward. I actually feel like precision recall are a little unintuitive. That's why I'm explaining it here. If you already know this, sorry, but it is a little unintuitive the first time that you've seen this. And I suspect many people who are coming into this more from a software engineering background have probably never seen this before. All right, recall. Recall is like a metric that's optimized around search. It's like how many correct answers did the model find? Like imagine I'm searching through all of my data to find the correct answers. And let's say I want to find 50% of them, like out of all of them. I don't know how many of there are, but out of all of them, I want to find at least half of them. Then I would target a recall of 50%. So that's kind of what recall is thinking about. It's like how many of all of the true correct answers do I want to get? Hopefully, like my goal is to get some correct answers in there, right? Train my model on some correct answers. So I don't want a recall of 0. Um, and then of course the issue is the precision recall trade off against each other, right? A really amazingly good model will have both high precision and high recall, but when we're starting out, we're still improving our model. Maybe a more modest model might have to sacrifice high recall to achieve high precision. So we might have to filter out a lot of good data, a lot of data to be confident that the data that we did select is high quality. Okay, and you can actually see the trade-off by plotting the precision recall curve, which is very straightforward to plot. sklearn has a very nice precision recall display library for it. I would strongly recommend using this library and not trying to plot it yourself because there are so many corner cases in the visualization of this thing that you should really just use a library for it. Otherwise, your figure's going to look weird and you're going to be like, why? And there are just a ton of corner cases you have to handle. So use this library. Don't just matplotlib it. Don't Excel it. Just use this library. Okay, but it's pretty simple. You like just record the labels. How many, for all of your examples, is this a correct example or not? You need to actually have some labeled data in order to generate this plot, so we're going to have to label some data. And then get the score. So we got these two arrays, and then we can produce our plot from that. Okay, and then we can use our plot to figure out where to set our threshold to. All right, and that's how we calibrate the model. So we went through the whole process of building this classifier thing. That sounds like a lot of work, but let's do it really fast. So now let's do it. Great. Okay, step 7. Let's build our classifier. From the previous step, remember I generated a bunch of QA pairs, training data. Let's go and look at that. My data, questions and answers. I generated how many? 2,400. Seems like a lot. And remember, I've thrown everything in here into this giant JSON. It's okay. Let's look at my starting point here. So there's a few steps I'm going to have to go through here. Remember, first I have to train my classifier. Then I have to run my classifier. Then I have to calibrate my classifier. And finally, after I've done all of these things, then I can use it to filter out my data or like score my data so that I know what is the good data and what I should be training my model on. Okay, so here we go. Let's look at one step at a time. Train. It's the training script. Lamini classifier. I'm going to build my first classifier using 32 examples per class. I'm going to purely prompt engineer this thing. So here are some prompts for an incorrect class. Questions with incorrect answers. Imagine you're a medical expert reading the question answers about the ICD11 standard. Great. And here, my positive class. Questions with correct answers. Maybe these are not the most well-engineered prompts in the world. Sure, you could do better than this with some iteration, but let's just use this as a starting point and hopefully it demonstrates what we're doing here. We're going to prompt train it and we're going to save it. And, we already walked through the code of like what this thing is doing. So I'm not going to walk through it again. We already walked through it. The only thing I'm going to note here is like, okay, I'm going to add some data to it. If the data in our data set already has labels on it. So if it has this field in the JSON object called label, and the label set to 1, I'm going to assume it's a positive example, like a correct question with a correct answer. And if it doesn't, if it has a 0, I'm going to assume it is a negative example. And there may not be any labeled data, so I'm going to handle the case where there's no labeled data. Okay? And when I start out here, right now, there's no labeled data. So let's go. Like everything else, again, I like to use Docker. So I have a training script for Docker that's going to run that Python program. Here we go. All right, I have this on like ultra verbose mode. So you can kind of see what's happening here. Generate some questions with incorrect answers. Treats rare genetic disorder. Reduces, and I have no idea what these things are. Okay, but these are just some examples of like made up issues that this model is coming up with. Okay, here we go. Here's some longer ones. Reduces questions with incorrect answers. Now form a complete example. So we can see some of these things that come out of here. Let's look. Based on the description, here's a question. What is the ICD standard for diagnosing? I have no idea what this is. TNS deficiency? And here's an incorrect answer. Wow, the model really tried hard to come up with a very technical question and incorrect answer, but it did exactly what I wanted it to, okay? It has a question and it has an answer and it knows that it should be generating an incorrect answer given the question. Wonderful. So who knows how good this data is? We've already generated a whole bunch of data like this so far, but this is the data that's going to be used to train this classifier. So we're going to use these like piles of synthetic data on each side, some that are positive, some that are negative, and we're going to use our embedding logistic regression thing to try and draw a decision boundary between the two. Okay, so hopefully we can teach this classifier rating model the difference between correct and incorrect questions. But even if we can't, I'm going to show you how to improve the performance of this model. Okay, this is going for a while. If you don't turn on ultra verbose mode, I turned on ultra verbose mode just to kind of show you that. Let's see, how did I turn on ultra verbose mode? I think it was like this, logging, basic log level, equals debug. You don't turn on debug, it'll just print out a status bar instead of all this. There probably is a status bar in here somewhere, but this is just like the gory detail of every single example that got generated in here.
So maybe it's a good time just to like note something. Let me just kill it. Die, die, die. Let's try running it again. Um, let's see what happens. Okay. You saw how I kind of like killed that and restarted that. Sometimes because we're connecting to servers like over the internet, sometimes the internet connection, we just like lose the internet connection. Lamini does have a pretty sophisticated caching system. So even though I don't have any kind of like automatic support for like restart, if I run into any issues with this, I could just run it again and it kind of very quickly got up to the same point that it was at previously. And then we eventually finished here. So it's okay to basically like kill your jobs and restart your jobs because we have a pretty sophisticated caching system. And if you've already have like results that have been submitted, you'll probably be able to hit them in the cache. And so even if your internet connection goes down, I'm on vacation, who knows what my internet connection is like. While you're running one of these scripts and you're like, oh no, I don't want to restart it, just restart it. It should be okay. If you're really generating an enormous amount of data, I would recommend putting in some like persistence things like I put in the previous script. You saw that question generator thing. Um, the ability to like save your progress and restart, or maybe you want to run that thing in a batch job, maybe not on your laptop if it's really going to be running for a week. Probably don't want to run that on your laptop. Um, the training system, like where we submit training jobs, that automatically does get run in a batch system. So you can like submit a training job and it's like, oh no, it's going to take a month or something. Just let it go. It'll be okay. You can turn off your laptop. But some of these other ones, right? These are more like because I'm just like submitting batches of requests and I'm kind of like building these like batch jobs on my own. You might actually want to run these in like a batch kind of framework, on your end, but it's on you to build that. Okay, so we train a classifier. There it is. It's saved. Um, let's try running it. Let's try like using it to classify all of our data. Let's see how that works. Docker. Okay, let's just look at our script to do that. Classify. You're right. So we're going to load the one that we just classified. We're going to load our data in batches. Right. So again, we're going to batch pretty big batch size. And then we're going to use the model to predict. So here, let's just look at the API on that so you can see it. Okay, we've got question plus answer. That's basically the input to our classifier. It's a string, right? The question plus the answer is a string. And we're going to classify it, and we're going to get some probabilities out of there. So we're going to just store the whole thing. This thing returns like the detailed information for each class. And, in the spirit of saving all of our data, we're just going to store all of it into a JSON lines file called predictions.jsonlines. Okay, let's do it. Docker. Classify all of our data. There we go. Remember these are, oh, actually, I guess this time I'm printing out like individual elements here. Okay, so this thing's got to get to 2400. All right, and again, this is slow because I'm running this through an LLM, right? There's an LLM that's actually generating all of the embeddings, the intermediate state that I'm using in this classifier, and that's why, 50 QPS, not too bad. Not too bad for an LLM running like a, big Mistral class LLM. Um, there we go. Classified all of our data in 47 seconds. Let's see. Let's look at it. Predictions. Okay. So is this thing correct or not? Well, see, we have class ID, class name, incorrect, probability, 38% correct, probability, 61%. Okay. So we did this a bit. I want to run a first pass on here of filter, right? So who knows how good that classifier was? It's hard to tell, right? Because there's so much data. Um, if in order to do calibration, we need some labels, right? We need to kind of have some ground truth reference of what is, correct or incorrect. So let's first run this filter program. And I'm just going to set the threshold to some default like 0.5. Okay. So I'm going to load predictions. And then I'm just going to save the ones that are higher than the threshold. But also I'm going to save them in a sorted order. Okay. So that the ones at the beginning of the list are going to be the most likely to be correct, and the ones at the end of the list are going to be the least likely to be correct. And I'm going to use this to help me with labeling. So I'm going to use an approach here. It's usually called active learning, where I'm a human and I'm kind of working together with this classifier to label my data. So it'll become more apparent how this works as I do it. All right, I'm going to run filter. I didn't do calibrate because I don't have any ground truth. Filtering is, of course, blazingly fast because I'm just like loading some strings. Okay. So, got about half my data. Okay. Let's take a look at it. And also, it's actually just printed out in like a realistic kind of a format. Let's see, it's going to be sorted, right? So I think I can just look at it, filter predictions. JQ should have question, comma, answer. Let's look at it. Okay, here we go. What is the recommended dosage for alfentanil in adults? According to the ICD standard, the recommended dosage is not specified. Well, that's not a very good one. I don't think so, right? I don't think that was very helpful. But okay, so what I'm going to do here um, is what I'm going to call error analysis. So in error analysis, I, as a human, am going to go and look at the results that the model has produced. These are multiple models here, right? I have my question answer generator model and I have this classifier model, right? So I'm going to look at these results and I'm going to try to read through these and develop an intuition, just like in debugging. This is like triaging and like software and debugging of like, I want to know like why the model is not working correctly. So I want to look at the answers, questions and answers here, and I want to say like, okay, first of all, like, are they correct or incorrect? And then if they're incorrect, I want to not just know that they're incorrect, I want to know why they're incorrect. And I want to form an opinion about systematic reasons why questions and answers are incorrect. And so if I have like an idea of a systematic reason, then I will have the ability to go back and fix it by, in a simplistic way. I'm just going to label some examples, like some positive and negative examples, right? And because I'm doing this in this kind of like sorted way, I'm like, oh, I'm looking at, oh, these are if there's an error here at the top of the list, this is going to be an important error. This means the model is really messed up, so I really need to fix it. So I'm going to look at high severity errors, and also I'm going to try and get categories of errors. So if I could fix like an entire category of errors, then I could make the model a lot better than if I just like keep improving its performance on something it's already good at. Okay, so that's what I'm going to try and do here. This is error analysis. In order to do error analysis, you need to look at the data, right? I'm looking at the data and reading through all this here, as you can see. So let's just watch how it goes. Okay, this one wasn't great because it basically says I don't know, right? It's like, I don't know, you should take into account these different factors. It's not an incorrect answer. It's just not a great like thing that it's teaching the model. But let's look at some other examples. Let's see if we can find some more really bad examples. All right. What are common symptoms of tuberculosis? Depending on the site. That doesn't look wrong to me. I'm not an expert in tuberculosis, so that doesn't look wrong to me. Let's keep going. What's the difference between episodic and continuous substance abuse? Okay, I'm just going to keep going through the questions. So here we go. Possible outcomes of obstructed labor. Ooh, okay. Let's keep going. That one also doesn't sound bad. Recommended dosage of treatment of malaria. That's okay. What is the definition of pneumothorax? It's okay. These are actually okay. So let's see. Symptoms of abscess of the liver. Duration of time required to diagnose. How was tuberculosis transmitted? Let's see. Let's keep going. What is definition of a general medical exam? Hazardous drug usage. Some of these are kind of vague, so I'm just like noting like some of the questions seem like a little bit vague. What is the purpose of dialysis devices? So let's go a little bit more. What are the consequences of using firearm pellets? What are the symptoms? What are complications of malaria? What are the different types of behavioral patterns? What is the purpose of a bullet or pellet? Okay, that actually seems okay. Let's go a little bit further down. Maybe we can find some others that aren't super clear. Actually, why don't I just look at the questions? It actually looks like some of the questions are just somewhat vague. So I'm going to start with this hypothesis of just after looking at that, I have this hypothesis that some of the questions are kind of vague. So let's look to see if we can find like groups of vague questions. Okay. Um, like this one, what is the purpose of the door, window, or related fitting? Okay, so maybe someone got injured on a door, but like the problem with something like this is that it just doesn't have enough like context in it to really know that. So I'm going to say that's not a really good question just because it's a question that doesn't have a lot of like good context in it. All right, so there we go. There's a good example. So now let me go back to my data. Data. Oop, classify data. All right. So I think I can just put this one back in the beginning. Okay, questions and answers. Find it. Whoop, there it is. Let's add a label. Label. Remember, 0 means I don't like it. Okay, I'm gonna label it as I don't like it. Incorrect. Bad question. And let's see here. Where did it come from? Oh, okay, there was a code related to, I mean, you can kind of see why this happened, right? This entity, it's probably like somebody got injured again, like on a door or window or something, and there's a code for that. But this entity in ICD just doesn't have a lot of like information in this description. So when you ask the model to generate a question based off of this, it just doesn't have a lot to go on. So I'm going to say that's a bad one. Okay, that's something. Let's keep going. Let's see if we can find more examples of this kind of category of like, all right, I really didn't like that. Because it was too vague. There wasn't enough information really to help me. What is the purpose of charcoal activated? I also think that one is pretty vague, but let's see if we can find some that are even more vague. I'm gonna go down a bit. There we go. Here's another good one. What is the typical testing method for evaluating safety and performance in this code? Well, I clearly don't have enough context to know what this code is based on this question. So can't answer that one. Okay, let me label that one as bad. I don't like that one. Okay, didn't like it. Let's see if we can find some more. Okay, there we go. We got some more like that. What is the name of the specific type of malaria being referred to in this code? Let me get rid of that one.
You didn't tell me what code it was. So now I have like actually a hypothesis for how I could do better um, better prompt engineering. I should probably say something like, if the code is included, reference it. Like if the code is necessary to answer the question, then include it in the question. Something like that. So I could fix that in the future. I'm just going to remember that. But let's see. I can find more things like that. They're just too vague. All right. I mean, a lot of them do have at least the word ICD in them, so that's something. What is the context in which the examination or investigation is performed? There's another one. So I don't know what the examination or investigation is. I'm sure that's meant to be like a very specific one that makes sense for an entity. Here we go. Oh, or maybe not. This one probably just needs, like again, a lot of these things look like they need more context. This might be fixed by, adding in some of that like parent-child kind of thing. But let's see. See if we can find a couple more examples of that. What is... Wow, I'm not sure I want that one. What are the symptoms of green sea turtle seafood poisoning? That's very specific. Some of these are hilarious. Um, so you can have one of the coping mechanisms that you can probably have during labeling. Labeling is the least favorite activity of anyone, especially a software engineer. Um, so you have to find ways of keeping yourself entertained to not lose your mind. Okay. Whoa, I'm not sure I want to know what this one is. What is the purpose of the washing machine, according to ICD11? Wow. Let's see. Hmm. What is this one? Code. XE4FB title washing machine. Clearly not enough to go on there. I like this model generated answer. According to the ICD-11 standard, the purpose of a washing machine is to clean clothes. That's really good. Sometimes language models are hilarious. Um, okay, near misses are usually hilarious in language models, so not enough context. All right, so now I've gotten a few examples where I just don't have a context. So now I got the negative examples. Now I want to label some positive examples because my classifier probably needs like some positive and negative examples. So let's find some really good examples where I clearly have enough context. All right, what is the recommended dosage of, I don't even know what that is, to treatment of malaria with this particular code? That sounds like there's a ton of context in there. So let's find that one. And I want to label that one. Oh, I've already labeled it one. Interesting. Thought I got rid of all my labels. But anyways, label one. Great. No wonder it's so high up there. Um, let's see. What's the purpose? No. Let's find some that are like even more specific. Yeah, let's go down and find some very specific ones. What are symptoms? Maybe not. Here we go. This has a code in it. What is the purpose of communication devices associated with adverse incidents as per this code? Let's look at that one. Let's just look to see if it's good or not. Uh, I think the model is just making this answer up, so I'm actually not going to label that one as a good one. Um, let's keep going.
Okay, let's see this one. What is the indication for use of the medication being coded? Let's look at that. All right, title is obstructive sleep apnea. Is that right? Let's go and check that out to make sure that's right. Brand, taken by mouth. What is the purpose of this thing? With familiar, I don't even know what this is. Intrahaptic, let's see what that is. Liver disease. Ooh, no, I don't think that's a good one. Let me just also label that one as bad because that's just an incorrect answer. Okay, but let's keep going. Got like some positive examples. What is the location of the burn described by this code? Let's try that one. Location of the burn. Burn of, title, burn of trunk, except genitalia. Full thickness burn. Okay, that one seems fine. As long as the answer is not terrible. Let's see, answer. Of the burn is the trunk. Great. Thank you. I like that one. So let me go to the end. 1. Correct. All right, let's find a few more. What is the purpose? So let's just see. What is the name of the mushroom? Name of the mushroom. Oh, okay. Lepiota fulvella mushroom. Interesting. It's got to be either a good or a bad mushroom. I'm not a mushroom expert, but it's clearly referenced in the entity. Okay, let's do 2 more. I'm not even sure that is ICD. I'm just going to skip that. Okay. What is the name of the vein being referred to in XA4ZZ3? Maxillary vein. Does the model answer maxillary vein? Is the maxillary vein. Great. That's correct. It's easy when the answer just is included directly in the entity. Okay. Let's get a couple more, or one more. What is the therapeutic class of tizanidine? That's pretty simple. Ooh, opioid analgesic. I'm gonna have to look that one up. Skeletal muscle relaxants. That's got to be good. Okay, we're getting close. Is it opioid? Drugs.com. Works by blocking nerve impulses. I mean, is it an opioid? Isn't a narcotic. It's a muscle relaxer. It doesn't. Okay, so no, not correct. It is not an opioid. Whoops. Sorry, model. You hallucinated that one. What is the definition of a person riding an animal of any type? What is included? The standard is just pretty weird. Okay, here we go. Let's try this one instead. What is the purpose of the code PKO1? Classify the use of firearm pellets. Okay, let's just see. Use of firearm pellets during armed conflict. Great. Sounds perfectly accurate to me. Included in the entity. Wonderful. So we've got some positive data, we've got some negative data in our questions and answers. So let's go through this again. Okay, let's run Docker train. It's going to reload, my new labels that I had in there. Remember, I already had some code in there to do this for me. So this is going to help. The synthetic examples that are going to get generated here are going to now base themselves off of real examples. They're going to follow the prompt, but they're also going to try to follow real examples or be, similar to real examples. Okay. Here we go. Coding error. Thank you. Question pertains to incorrect coding of medication. Wonderful. All right, got some incorrect answers with codes that are hallucinated. Wonderful. So the classifier is generating some synthetic data. They're becoming more medical related. They're starting to look a little bit better. So hopefully this classifier is now improved with our, limited amount of labeling. Just note there, I didn't have to label the whole data set. 2,400 examples would have been really bad, but I did look through a lot of it, and I was also looking through it in sorted order. So I was trying to find like egregious errors that the model was making. So even though, again, I didn't assign labels to very many things, probably assigned like 10 labels, I looked through a lot of data. Maybe a few hundred examples I looked through, just scanned, cursory examination. The human visual system, right? I have them all on one page. I had like, 30 of them on a page. Humans can take in a whole bunch of information like that all at once. So trying to be efficient with labeling. Okay. So also, here I'm doing synthetic data generation. Here we go. Generating more data. Hopefully we're getting close to the end of training this thing. All right. Training is complete. Let's run it. Classifying our data again. I think this took like about a minute last time. Just as one note, like everything else in machine learning, this is iterative, right? So I can like keep going through this and keep improving the quality. And like once this model gets pretty good, I can crank up the amount of data that I push through it. As I crank up the amount of data, I could tune it towards higher precision so that the quality of the data is further improved. So even if I'm not like labeling data, one tool that I have is I can label more data. That makes my model classifier better, my reward model better. Another tool that I have is I can kind of crank up the scale, like just throw a huge amount of data through this and tune it for higher precision. So that's also going to help. So these are ways that I can use to you know, kind of generate like this big amount of higher quality data. Okay, but let's look at calibration. We still haven't looked at calibration yet. We need to do this. Okay. What is now we have some data, so now we can do calibration. We already looked at the source code for this a bit. What the hell just happened? Sorry. Okay.
Sorry about that. Let's keep going. All right. So we're loading our data that we've classified. Make sure it's got some classifications in there. Make sure it's got some labels. And we're going to plot this precision recall curve. Okay. And we're also going to compute the threshold for 90% precision. Okay. Let's see what it looks like. Also, just note, one of the things that I did here, I violated one of the core principles in machine learning. Don't train on your test set. I'm evaling on the test set as we speak. Or sorry, yeah, that I trained on. This is one of the mortal sins of machine learning. Well, I'm doing active learning right now. So that means that I'm going to generate some more labels as I go through this. So um, what's going to happen right now is it's going to, but let's just see what happens. I'm going to commit one of the mortal sins. What happens? Run calibration. If you don't understand what I'm saying, like just bear with me for a second. Okay. Hooray. I generated a precision recall curve. Let's open it up. There we go. Precision recall curves should kind of look like this. They should start high over here, they should be high over here, and then they should go follow along like that. Now, again, I committed a mortal sin. So this curve is like unreasonably good, right? It means like, oh, this bottle is perfect. It's not really perfect, it's just really well fit to the data because I trained it on the labels. Okay. And I wanted to train it on the labels because um, I did want to like actually, do that level of filtering. But now, basically what I need to do is I need to do like a little bit more labeling. And uh, the when I do a little bit more labeling, that curve is going to become like less overfit. Okay. And again, the reason I'm doing it this way, I'm not having like a strict training and test set and like having a clean separation between these things, is because I'm doing active learning, which means I'm trying to improve this kind of in an iterative way where I keep editing my data and like relabeling my data. Okay. So we're going to this again. Okay. Oh, I got less, but actually, that's fine. That's helpful. So let's do it again. Let's look at my questions. Are all of these good? So if these are good, I'm going to actually label them in here. Let's see, are the top of my list good? What are the possible outcomes of injury of blood vessels at the neck level? Let's look at that one, see if that one's a good question to answer. My data. And this time here, I'm going to actually edit the predictions so that when I do calibration, I'm going to pick this up. Okay. Answer: death, coma, persistent vegetative state. Is that true? Unspecified. Not so sure. It's not really specified. I'm going to say no, not good. But actually, let me just see if this is reasonable or not. Of course, it depends on this thing, but blood vessels at the neck level. Injury of blood vessels in neck. Life-threatening complications. Vascular trauma. How can it? Blood can clot. What are causes? Neck trauma. Here we go. discomfort, Werner's syndrome, stroke-like symptoms, blurred vision, dizziness, severe pain. I feel like this is not a great answer. It's not consistent with like just a general reference on the internet, and it wasn't in the reference material. So let's just say no, I don't like that one. Label no. Okay, it's fine. Recommended dosage. Okay, this might have been one that we labeled, but let's see. Yes, one we labeled. Skip it. Possible outcomes, complications, other injury of internal jugular vein. This thing, answer. They're not explicitly listed. Complications that are related. I'm okay with this one because it's not listed. Okay. Recommended dosage of hydroquinine. Ooh, I had that once. That was not pleasant. Lots of hallucinations. Let's see. Recommended dosage. It's not specified. It provides, let's just say, side effects, dosage, depends on all sorts of things. Great, I like that answer. Function of this joint. Temporomandibular. Lower movement of the skull, is that correct? Fine, that was just a factual question with a factual answer. Thank you. Correct answer. Great. All right, so we got some correct answers in there. Let's go all the way to the bottom. Is this thing right? What is the code for bungee jumping? Code. Wow. It's correct. That is the code for bungee jumping. All right. Definition of no loss of limb. Seems kind of a strange thing. Deep. Okay. Wait, what? No loss of limb. Title. Deep fold thickness with no loss of limb. Complex burn. Default. No, that one just doesn't have enough context in there to know it's about a burn. 0. Let's look at some others up here. Rupture. What is the code for rupture of pulmonary vessels? That sounds pretty straightforward. Hopefully that one's pretty clear. Code for rupture of pulmonary vessels. Rupture pulmonary vessels. Great. And what is the answer? Answer, come on. B. BO2.2, BBO2.2. Yes, that is very correct. Correct. All right, let's get some more. Let's get a few more. What is the definition of pH 00? No idea. Let's find out. What is it? Answer. Code for injury caused by being struck by a blunt object with undetermined. That is correct. Okay. All right, we labeled a bunch of data now. So now let's try running calibration again. Get a new plot. Great. My threshold moved a little bit. Let's look at my plot. Now my plot looks much more realistic. Okay, so somewhere in here, I need to rerun this classifier, but basically, here's a new threshold. Wait, 90% precision, is that right? Just this one. Oh, I think what's happening here is that's just max precision. Is that right? Oh no, maybe there's a 0.9 in there. Oh, there is a 0.9 in there. All right, great. There we go. So, um, I went back through and calibrated my data. Let's do the filter. Okay, filter. If I label a bit more data, I become more confident in my, calibration. But let's just do that. That one. Go through my filter. Filter again. Okay, I have much less data, so I'm more confident that that data, is higher quality. But I also have more, at this point, I have more labels. So I can copy my data predictions, which I added more labels to, into my data questions and answers. So we get the labels in there, and I can run classify again. Let's do this one last time. The main thing I'm trying to demonstrate here is like you can invest more time into this, just following this kind of approach that I'm going through of like looking at the answers, like calibrating your model, filtering it out, looking at the filtered data, running error analysis, like looking at the data, seeing what's right, what's wrong about it, like finding the problems with it, labeling the problems, repeating the whole thing. It's an iterative process, and in this iterative process, I am building a better reward model. So this classifier just keeps getting better. Okay, it's more grounded in the ground truth. And I'm using these kind of like powerful technologies of like data augmentation and like an LLM and active learning in order to kind of get this thing going. Oh, sorry, I ran classify. I should have run train. My bad. Training it one more time. Actually, I'm just gonna let me kill this thing. It's really annoying to just look at all that stuff all the time. So I'm gonna comment out this like logging message, and we're gonna just look at a status bar. There we go. Makes way more sense. Yeah, again, that was just to give you some intuition about it. I'm going to go through this one last time. But while I'm doing this, while I'm like waiting for this to finish, the last thing to do here is like, well, I can close the loop on this. So now I can take my reward model with all those like good questions and answers, and I can feed it back into my fine tuning step. Right? So I was training this thing. I was playing around with some hyperparameters, but I was training this thing on, my saved questions and answers. Well, now in here, my classifier, I've got filtered questions and answers, right? I've got only the good ones in here. These are filtered out, like based on my quality goal, 90%. So a simple thing that I can do is I can just feed this file straight in this training script. And now I can fine tune on higher quality data that has been selected and optimized by my reward model. And now I have a data pipeline set up, right? Like I generated all this stuff. Remember my generate data script? I generated all this stuff. I can do prompt tuning on it, right? So I have some ideas about like how I go back and improve the prompts to like improve these questions and answers. I really want to make sure that the question has enough context to be answered, and also that the facts like come like directly out of the entity in there. Like we do, the model shouldn't try and like make things up that aren't in the entity. My classifier is already kind of filtering that out, but I could also probably, kill it at the start over here. I probably do want to go back and include that like parent-child information. Some of those codes, like obviously they kind of like needed to know what it was like the code was a modifier, so you kind of need to know what the parent was in order to be able to generate a good question on it.
So there's a lot of ideas I have to like keep improving this stuff. And um, now this is really just set up like as a pipeline. Like I can just make these changes, I can just run it. The model is going to get better. I can launch training jobs. It can get better. I have it like hooked up in a RAG application, right? So I can go back into RAG and just like slackbotted RAG, slackbot RAG, right? I have a model that I'm using, base model, RAG model, using the base model. Well, now I have my, where'd it go? ICD11 v0 model, ICD11 v0. So now I've hooked up my fine-tuned with my reward model tuned data. I've hooked this all up back together, and this complete app, it's deployed, right? Like this is an app that's actually connected. People can submit requests to. This whole thing is like um, it's all hooked up together. So if you made it all the way through to the end here, this is really the end. There we go. We trained it. Classify. You made it all the way through to the end here. You've learned a lot of really powerful tools that can help you build your own language model, right? Like this is a data generation engine. We added some initial data like ICD11. We can now expand it and augment it and inject it into the language model, both through RAG, through prompt engineering, through instruction fine tuning. We can augment the quality of that data using classification, right? Using this reward model we just built. And we can evaluate the quality of the new models that we produce and show, that they actually are better than the ones that we had before them. Um, so these are the main tools that you need in order to build your own language model and like deploy it and integrate it in with your own application. Also note like all of this stuff is exportable. So, hey, you spent all this work building this model. It's a really good model. You want this model. Just download this model, right? Um, if you're a company, probably want to keep it like internal as IP, but if you're a researcher, if you're an open source developer, go publish this model on the internet, right? Hugging Face has um, 500,000 models almost. They could use 500,001. Um, and especially, I think we're just starting to scratch the surface of like all of this information that's available out there that's inserted into these models. Like, as we just noted here, ICD-11, very important, very widely used medical standard, is just completely unknown to these models. This is not the only type of information these models don't know about. Um, so there you go. You have all the tools that you need to build your own language model. So let's see what you do. All this code is going to be available open source along with this video. Again, feel free to modify any of it. Again, I build everything here on top of Lamini because all of this stuff under here assumes I have like a giant GPU cluster. That's why I was able to generate all this data and classify this data, right? Like when I ran classify right there, 50 QPS through an LLM, that's needs a big machine underneath it. So you got to supply the machine somehow. So wherever you want to do it, go for it. Build your own. I love building. Hats off to all the builders out there. And but here, let me just actually finish this off. Docker, calibrate. Again, mortal sin of machine learning. It's gonna be about the same. We can look at a fake but like great looking precision recoil curve. But actually interesting. Looks like it's hard to classify some of this stuff. It's kind of interesting. So I may actually have to back off my threshold pretty far over here, right? Like if I wanted like really good examples, I'm gonna have to back off
my threshold to, where is it, my ones go? 1, 2, go out to 1, 2. Oh, that's what it was. That was the one it selected. I have to back off my threshold to 0.49. Let's do it. Filter. Back off that threshold. Oops. Some of these things are, this is why calibration is important. These numbers are very hard to interpret, right? So like the difference between, I don't know, like let's just go back to our curve. Like the difference between like this point on the curve and this point on the curve is, it's like the difference between this number and this number. What? It's not linear. The point is, like, obviously this graph is not linear, but also the thresholds are not linear. So one of the reasons why we want to do calibration using a method like this is because these thresholds are just like highly unintuitive. Okay, but let's run it. Doc. Filter our data. All right, I've got 1,000 examples. They should be sorted. Now let's go and look at them. Do I like them? Possible outcomes of other jugular vein injury. What is the definition? A lot of jugular vein stuff is up here. What is the purpose of this code? What is the category of inner injury unintentionally struck by a projectile? Let's look at them with the answers also. All right, let's look. What are the codes assigned to superficial industry of the wrist or hand? NC51. Let's see. Superficial industry of the wrist or the hand. Wonderful. All right. Looking good so far. So we got some high quality data. Now, I'm probably also going to run this for a while and try and post this data set so that, if you're a machine learning researcher and you have like a model and you want to produce like a really good ICD medical model and you can do fine tuning, you'll have some data. And again, I'm going to post this whole pipeline. So if you want to further improve this, go for it. Excited to see what people come up with. Also, of course, worth noting, I did this for ICD11. We've done this for all sorts of different applications. I think as long as you have like a pool of data somewhere, in a data lake, just a pile of docs, relational database, you probably have all that you need to follow the exact same process. Of course, you're going to have to adapt every single step in here, but the skeleton, like all the steps that we went through back here, all these steps, wire up an application so you can actually use it. Don't forget about deploying it. Deploy first. You can make some improvements to the model through prompt engineering. We've used prompt engineering in every other step over here, so it's an essential foundation. RAG, you can look up information, relevant information. One of the other really good things about RAG is like you don't have to run these like giant pipelines, if that makes sense, other than running the index. Again, that's still an LLM, so it's still kind of expensive, but at least you don't have to run a giant training job. So it could be like more real time, maybe like a little bit more up to date, maybe. Although fine tuning isn't that expensive either. Um, okay, fine tuning, you can train your own model. We showed how to like transform the data into a format that we could use to train the model and to actually run training and get structured information out of it. We use that for evaluation. We also used it for classification. We need to do evaluation so we know that our model is getting better and we can measure that. And classification, we saw how we can use that, flow that I just went through to build a reward model. So all of these steps should apply to many different problems. And so, yeah, I think just excited to think about all of the different applications that people could build on top of
on top of LLMs. Um, I really personally think of like after we discovered LLMs, um, LLMs are almost like a new computer. They're almost like a new programming language. You know, you could build all sorts of different applications on top of them. It's pretty exciting. So let's look forward to the future where the LLM is the computer. All right, I'm gonna stop. Bye.